At the center of the Milky Way, our black hole is doing something it shouldn't, flickering like a wounded star, twisting light into impossible shapes. Every pulse from Sagittarius A star feels like a message, and the timing is wrong. Is this a glitch in space-time, or the first crack in what we think a black hole is? In the Milky Way's buried core, the laws of nature are being stress-tested at their breaking point. Sagittarius A star is not just an object, it is a courtroom where gravity must testify under oath. From Earth, the galaxy looks serene, a bright river of stars, indifferent to our questions and our clocks. Yet toward its center, dust closes like a curtain, and visible light simply fails to arrive. To see what lives behind that curtain, astronomy changes languages. Radio, infrared, and millimeter waves become our eyes. We do not watch the center directly. We reconstruct it from fragments, delays, and polarization, an image assembled from what survives the journey. At the heart of that reconstruction sits Sagittarius A, 4 million solar masses pressed into a region smaller than our solar system. It anchors the orbits of the S stars, bends time for anything that dares to pass close, and turns space into a lens. And still, amid all that certainty, one stubborn feature refuses to behave like a mere footnote. It appears, disappears, and returns with a kind of structure that should be erased by chaos, suggesting either an overlooked order in the maelstrom or a deeper rule we have not named. This film follows the anomaly the way scientists must, not as a myth, but as a chain of measurements. We will build the baseline that general relativity predicts in strong gravity, then ask which parts of the signal belong to instruments, to plasma, and to the black hole itself. Because in this region, near is a dangerous word. Near means minutes of orbital time, extreme magnetism, and matter heated until it becomes a luminous, turbulent fluid. Near also means that light can loop, stall, and return, carrying information that has been edited by curvature. If the anomaly is real, it is not merely a curiosity at the center of our galaxy. It becomes a lever, capable of prying at the boundary between classical gravity and the quantum world, and at the question of whether horizons are as final as we say. But before we reach for new physics, we will do what the best investigations demand. We will try to make the mystery disappear. We will test whether the pattern can be forged by calibration, by sparse sampling, by Earth's atmosphere, or by the restless weather of plasma that swirls around Sagittarius A. And if it survives those trials, we will widen the hypothesis space without abandoning rigor. We will consider what else could mimic a black hole's mass and silence, while subtly changing what returns to us. Objects that look almost identical from far away, yet differ profoundly at the edge. Every step in this journey is a wager against our own expectations. Either the anomaly is a rare window into the most violent, hidden dynamics of warped space-time, or it is the first sign that our clean equations have left something out. In the end, the central question is not whether the universe is strange. It is whether the strangeness is only in the plasma and magnetism we can model, or in gravity itself, where time, information, and reality may not agree on what inside means. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin by finding the glow where nothing should shine, then assemble the black hole blueprint that makes an anomaly unmistakable. From there, we follow the data trail to the frontier, where weather in space-time competes with the possibility that horizons are not the final word. The Milky Way looks calm from here, a pale river of stars arcing across the night. Yet its center is sealed behind dust, wrapped in soot-dark lanes that cut through the bright band. Visible light dies in those long, cold corridors between us and the core, absorbed and scattered by grains no larger than smoke. The place that should be brightest becomes a blind spot, and that absence is the first clue. To reach the galactic center, astronomy changes languages and listens in other bands. Infrared slips through dust that blocks starlight, because longer wavelengths weave between grains instead of crashing into them. In infrared images, the sky toward the core stops looking empty and becomes crowded, with dense star fields stacked in depth. Hot gas glows there as well, warmed by shocks, collisions, and the slow grind of gravity. Radio waves travel farther still, tracing magnetic fields and compact sources we cannot resolve optically. At some radio frequencies, even the dust itself becomes transparent, and the galaxy's hidden architecture begins to show. X-rays arrive only from violence, from shocks and particles pushed to extreme energies. They come from electrons spiraling in magnetic fields, or from gas heated to millions of degrees as it plunges inward. They also carry the signature of absorption, because intervening material bites chunks out of the spectrum. Each wavelength is a partial confession, and the full story requires all of them. The galactic center is not one picture, but a layered composite assembled from different kinds of light. At the heart of this obscured region sits Sagittarius A, a compact radio source first noticed as radio astronomy matured in the 20th century. It is small on the sky, almost lost amid brighter structures, but it anchors the galaxy's gravitational map. Early surveys could not see a black hole directly, so they searched for the consequences of one. For decades it was a candidate, a suspicion built from indirect evidence and careful patience. Now it is the best nearby laboratory for supermassive black hole physics. Sagittarius A star is associated with a mass of about 4 million suns. That number is not guessed from brightness because the source is faint and variable, and much of its power emerges outside visible light. It is measured from motion, from stars that orbit an invisible center with clockwork precision. Their paths turn gravity into geometry, and geometry into a mass we can trust. In practice, astronomers fit orbits, infer the central pull, and watch the same stars return on schedule. The most famous of these are the S stars, fast and close, tracked year after year as they thread through the crowded nuclear star cluster. One, called S2, completes an orbit in roughly 16 years. At closest approach, it moves at thousands of kilometers per second, deep in the central potential, where relativistic effects begin to matter. Its orbit closes around empty space, and the emptiness behaves like a single, compact object. The star's light even shifts slightly in frequency near pericenter, a subtle nod to time dilation and gravitational redshift. The orbits do more than weigh the center, they constrain its size. If 4 million solar masses were spread across a star cluster, the cluster would glow, and it would not stay stable. If it were a swarm of dark objects, it would evaporate and scatter over time, because close encounters would fling members outward. The simplest survivor is a black hole, or something that mimics one almost perfectly. The evidence is not one measurement, but a convergence. Many stars, many epochs, one gravitational focus. A black hole is not a hole in the usual sense, but a region where escape becomes impossible. The event horizon is the boundary, the point of no return for matter and light, defined by the geometry of space-time itself. Outside it, photons can still leave, though their paths are bent and delayed, and some are trapped in looping trajectories. Near it, gravity reshapes time itself, and the rules become unfamiliar. What looks like a place in space is also a change in what future means for anything that falls inward. Near the event horizon means close-in units that ignore kilometers and use mass instead, because mass sets the curvature scale. For Sagittarius A star, the horizon scale is comparable to the orbit of Mercury, packed into a region far smaller than our solar system. That comparison is deceptive because it compresses a familiar distance into an extreme environment. The distance is tiny, but the consequences are enormous, because space-time curvature rises sharply there. That is where general relativity is tested hardest, and where surprises are most valuable. Yet Sagittarius A star is not a steady beacon like an active galaxy nucleus. It is underfed, accreting at a trickle, compared with brighter quasars, because little cold gas reaches the very center. Much of what does arrive may be blown back out by turbulence and magnetic pressure before it can fall in. Most of the time it glows weakly in radio and infrared, with a low, persistent hum. Then it flares, briefly, as if a switch is thrown in the inner flow. Flares are expected in turbulent plasma, and variability is not itself strange. In a magnetized accretion flow, fields twist, reconnect, and snap into new configurations, dumping energy into electrons that radiate efficiently. What is strange is a newly reported pattern that repeats too cleanly to dismiss. Observers describe a recurring signature near the horizon scale, seen across multiple instruments and campaigns. It appears as timing structure in flares, as polarization swings, or as apparent motion that does not match the simplest models. In some datasets, the flare peaks arrive with a quasi-periodic rhythm, not perfectly regular, but stubbornly clustered. The cadence hints at a preferred timescale, like an orbit, a precession cycle, or a repeating instability. In others, the polarization angle rotates rapidly, as if the magnetic field is twisting in a coherent loop. Polarization is not decoration. It is a compass that points to field geometry and to how light was processed on its way out. In still others, the centroid of emission seems to move on the sky in a way that resists a single orbiting hotspot explanation. Each clue alone could be noise, because the data live at the edge of what instruments can reliably measure. Together, they form a repeatable anomaly, the kind that makes observers argue late into the night. The key claim is not that Sagittarius A star is exotic, but that a specific behavior persists when it should wash out. Standard pictures treat the inner accretion flow as chaotic, with turbulence and reconnection creating brief, bright patches. Those patches can orbit, shear, and fade, producing variability without long memory. The reported signature suggests a structure that survives, or a driver that resets the system with surprising consistency. That matters because the near-horizon region is where models are most constrained and where the physics has fewer places to hide. The gravitational field sets preferred timescales for orbital motion, and those timescales can be calculated from the mass alone. Plasma physics sets how quickly electrons heat, cool, and radiate in infrared and X-rays. If the observed pattern sits in the wrong place or evolves in the wrong way, then either the plasma is stranger than expected or the space-time is. General relativity predicts how light bends near a black hole and how orbits precess. It predicts that strong gravity can lens emission into rings and arcs, and that time dilation slows clocks near the horizon. It also predicts that the horizon itself is featureless, with no surface to reflect light back outward. If a signal looks like it is bouncing, repeating, or anchored to a preferred direction, it forces careful checks. Some effects can be produced by lensing alone, yet lensing has a particular grammar that can be tested. The anomaly is presented as observationally grounded, not as a single dramatic detection. It is described as repeatable under different conditions, across different nights and different telescopes. It survives reprocessing and calibration tests, at least enough to demand attention, and that survival is part of the story. The question becomes whether it reflects the source, the instruments, or our assumptions. In frontier astronomy, the hardest step is separating a real pattern from a clever artifact. The observational scene is unforgiving because the galactic center is crowded and distant. Dust hides it, and the field is packed with stars that confuse measurements, especially when flares brighten and fade against a glittering background. The atmosphere blurs infrared images, and interstellar scattering smears radio waves, turning sharp structure into a softened glow. Even the best telescopes fight noise, systematics, and the limits of resolution. The target is not only small, it is restless. Every photon from the inner region is precious because the source is faint and fast. The relevant timescales are minutes to hours, so gaps in coverage matter, and weather can erase an entire night of opportunity. The emission is polarized, so small calibration errors can masquerade as magnetic structure. The source also changes with wavelength, so a flare in infrared may not match a flare in X-rays. Coordinated observing becomes essential, and interpretation becomes a puzzle with missing pieces. To attack that puzzle, astronomers built a toolkit that treats the galactic center as a multi-wavelength crime scene. At millimeter wavelengths, the Event Horizon Telescope links dishes across Earth into a virtual planet-sized instrument. It aims to resolve horizon-scale structure, turning interference fringes into images and constraints. For Sagittarius A star, it must also freeze rapid variability, which complicates every reconstruction. The data are not a photograph taken in one instant, but a synthesis assembled while the source evolves. In the near-infrared, gravity on the Very Large Telescope Interferometer measures astrometry with micro-arcsecond precision. It can track the motion of bright flares and map their centroid shifts over minutes, effectively watching light move in the inner gravitational field. It can also follow stellar orbits like S2, tightening the mass and distance estimates that set the scale for everything else. Gravity turns the inner region into a dynamic system rather than a static point. In doing so, it gives the anomaly a stage where motion can be measured, not merely inferred. In X-rays, Chandra and XMM Newton watch for high-energy flares that signal particle acceleration. X-ray bursts can mark magnetic reconnection events or shocks in the inner flow, where electrons are driven to energies that infrared alone cannot reveal. Their timing can be compared with infrared peaks to test emission models, including whether the same electrons produce both bands. X-rays also probe absorption and scattering along the line of sight, adding context to what infrared and radio see. When X-rays spike, they announce that something in the plasma has crossed a threshold. Long-term monitoring adds the fourth dimension, time across decades. It reveals whether the source changes state, whether flare rates drift, and whether any periodicity persists beyond a few campaigns. It also exposes selection effects, because we notice patterns more easily when we look harder and publish what stands out. The anomaly must survive this slow audit, or it will join the long list of false rhythms in noisy data. In science, persistence is not proof, but it is pressure. If the pattern is real, several explanations compete, and none are comfortable. It could be exotic plasma physics, with a stable magnetic structure like a flux rope, or a standing shock that keeps reforming near the same radius. It could be a precessing inner flow, driven by spin and frame dragging, imprinting a preferred timescale as space-time itself drags the plasma around. It could be a misread of radiative transfer, where polarization changes reflect viewing geometry rather than field changes. In each case, the challenge is to predict not just one feature, but the whole bundle of behaviors. More provocatively, it could hint that the central object is not a classical black hole. Alternatives exist on paper, from boson stars to gravastars to other compact objects without true horizons. Many mimic black holes in mass and size, but differ in how they handle infalling matter and how they emit near the boundary. A surface, even a dim one, could add echoes or phase-locked signals that a horizon would erase. The question is not whether alternatives are fashionable, but whether the data leave any room for them. The anomaly also touches fundamental physics, because Sagittarius A star sits in a regime we cannot reproduce. Strong gravity, relativistic plasma, and magnetic turbulence interact in ways that stress every approximation, from fluid models to assumptions about particle distributions. If general relativity is incomplete, deviations might appear first where curvature is highest and timescales are shortest. If it is correct, then the anomaly becomes a test of our plasma models and our inference methods. Either way, the galactic center becomes a laboratory that no accelerator can match. Cosmology enters because black holes are not isolated curiosities. They shape galaxies and their histories. If the nearest supermassive black hole behaves differently than expected, then our models of accretion and feedback may need revision, even for quiet galaxies like our own. If horizons are not what we think, then the story of information, entropy, and the early universe shifts. A small flicker at the center of the Milky Way could scale into a large correction elsewhere. The universe often hides its biggest lessons in its most compact objects. For now, the responsible stance is uncertainty with pressure. The signal is intriguing, but the environment is messy and the instruments are pushed to their limits. The same data that hint at structure can be bent by scattering, calibration, and reconstruction choices, especially when the source changes during the observation. The anomaly demands replication, cross-checks, and a theory that predicts more than it explains after the fact. It also demands humility, because the galactic center has fooled observers before. Still, the hook remains because the pattern repeats where randomness should dominate. Something near the horizon seems to keep time, or keep direction, or keep returning to the same track, like a metronome buried inside a storm. It is a glow where nothing should shine steadily, a hint of order inside turbulence. The central question is simple to ask and hard to answer. What is producing this recurring signature near Sagittarius A star, and what does it say about gravity and time? To understand what is wrong, we have to define what right looks like. We need the baseline picture of a black hole, an accretion flow, and the signals they should produce, including which features are robust against messy plasma details. We need to know which predictions are firm and which are flexible enough to absorb surprises without breaking. From here, the investigation begins with the standard model and then follows the data to wherever it leads. In the next step, we build the expected story, so the unexpected cannot hide in the shadows. To recognize an anomaly, we first build the baseline that should not be negotiable. Sagittarius A sits in strong gravity, where general relativity sets the rules for motion, time, and light. In the galactic center, strong gravity is not a metaphor. It is a regime where curvature is measurable. The mass is concentrated into a region so compact that Newton's approximations begin to fray at the edges. We are forced to use Einstein's language. Space-time itself becomes the stage, and gravity becomes geometry. General relativity replaces gravity as a force with curvature of space-time. Mass and energy tell space-time how to curve, and curved space-time tells matter and light how to move. That sentence is often quoted because it is elegant, but its consequences are practical and testable. The how to move part is a set of geodesics, the closest thing to straight lines in curved space-time. A planet, a gas cloud, and a photon all follow those geodesics, even though their experiences look wildly different. In ordinary life, curvature is so weak that the geodesics look like the lines we learned in school. Near a compact object, curvature steepens, and familiar intuitions fail. Distances, angles, and even the meaning of simultaneous events depend on the gravitational field. A ruler placed near Sagittarius A is not the same ruler, in a geometric sense, as one far away. Coordinates that seem natural at Earth become misleading near the black hole, where radial distance and time are not universal notions. Even the idea of a stable circular orbit becomes conditional, because the geometry itself can remove the possibility. This is why we build a baseline first. Without it, we misread the scene. One prediction is gravitational redshift, where light climbs out and loses energy. Photons leave the inner regions stretched to longer wavelengths, carrying a record of depth. Gravitational redshift is not the light getting tired, it is the bookkeeping of energy in curved space-time. A photon emitted deep in the potential well has a well-defined frequency locally, measured by a nearby clock. To a distant observer, that same photon arrives with a lower frequency, as if its color has slid toward the red. The deeper the emission point, the stronger the shift, and the more the spectrum is rewritten before it reaches us. Another prediction is time dilation, where clocks near the mass run slower to distant observers. Processes near the horizon appear slowed, even if locally nothing feels delayed. This is a subtle point that matters for interpretation. A flare can be fast for the plasma that produces it, yet looks stretched when compared to a clock far away. The plasma does not feel time dilation in the moment, because its own physics uses its own local time. But our measurements are made from the outside, where our clocks tick differently, and the mismatch is part of the signal. Light bending is the most visible prediction for imaging. Photons follow curved paths, so the black hole acts like a lens that can magnify and distort. In weak gravity, bending is a small correction that shifts a star's apparent position. In strong gravity, bending becomes choreography, with rays that skim the black hole, swing around it, and sometimes return toward the observer. The lensing is not symmetric if the black hole spins, and it is not gentle if the ray passes close to the photon orbit. A single bright patch of plasma can be duplicated into multiple images, each delayed and warped by a different trajectory. These effects are not optional details for Sagittarius A. They set the geometry for every orbiting clump of plasma and every photon that reaches Earth. They also set the scale of what we mean by close. For a 4 million solar mass black hole, the gravitational radius is enormous in kilometers, yet tiny on the sky. The relevant distances are measured in a few Schwarzschild radii, and the relevant angles are measured in micro-arcseconds. That mismatch between physical size and apparent size is why we need a planet-sized telescope. A black hole is called black because the event horizon does not let light escape. The horizon is not a surface that glows, it is a boundary in space-time. Historically, the horizon began as a mathematical feature of solutions like Schwarzschild's, and it took decades to be accepted as physical. It is not a wall made of matter, and it does not have a texture that can be photographed. It is an escape boundary, defined by the paths that light can and cannot take. Once a photon crosses inward, every future directed path leads deeper in, and that is what black means. That creates a crucial observational rule. We never see the hole itself, we see the environment that is heated and accelerated around it. The environment is an accretion flow, gas captured by gravity but held up by angular momentum. It spirals inward, heats through turbulence, and threads magnetic fields. Visually, it is less like water down a drain and more like smoke in a storm. The gas is ionized into plasma, so electromagnetic forces matter as much as gravity. Instead of sliding smoothly inward, the material circulates, collides, and rearranges, always trying to shed angular momentum. The spiral is real, but it is messy, and the mess is where the light comes from. Accretion is not a smooth drain, especially in a weakly fed system. It is a churning plasma, where density, temperature, and field strength vary with radius and time. If we could hover above the galactic center, the flow would look mottled and alive. Bright knots would appear where the magnetic field compresses and heats electrons. Darker gaps would open where plasma thins or cools, and then close again as turbulence mixes the region. The pattern would never settle into a single shape, because the underlying instabilities keep feeding it. In many galaxies, accretion is bright because gas cools efficiently and radiates away energy. Those active galactic nuclei can outshine their host galaxies. The history of this idea runs through quasars, discovered as star-like radio sources in the mid-20th century. Their enormous luminosities demanded a power source more efficient than nuclear fusion. Accretion onto a black hole provided that efficiency, converting gravitational potential energy into radiation with startling effectiveness. In those systems, the disk can be thin, dense, and luminous, and the spectrum can blaze across the electromagnetic band. Sagittarius A is different because it is unusually dim for its mass. For 4 million solar masses, its luminosity is tiny compared with a typical active nucleus. That dimness is itself a clue, because mass sets the maximum potential for power. If Sagittarius A were fed like a quasar, the galactic center would be a beacon, and the night sky would look different. Instead, it whispers, and that whisper forces theorists to explain where the energy goes. The baseline must include that silence, because it shapes every expectation about the plasma. The leading explanation is radiatively inefficient accretion. Much of the gravitational energy stays in the ions, is carried inward, or is lost to outflows. In a radiatively efficient disk, energy is quickly shared with electrons, and electrons radiate efficiently. In a radiatively inefficient flow, the plasma is so tenuous that ions and electrons can decouple. The ions can hold most of the heat, while electrons, responsible for much of the radiation, receive less of it. Energy can also be advected inward, disappearing across the horizon rather than shining outward. This family of models is often described as RIAF or ADAF-like behavior. The flow is hot, tenuous, and inefficient at turning infall into light. Hot, here, means something counterintuitive because the temperatures can reach billions of degrees. Yet the plasma can still be nearly collisionless, with particles traveling long distances before interacting. That changes how viscosity works, how heat moves, and how the flow organizes itself. The accretion becomes a laboratory for kinetic plasma physics, not just fluid dynamics. Low density matters because emission depends on collisions and particle distributions. With fewer particles, the plasma can stay hot while radiating little. Synchrotron emission depends on energetic electrons, but it also depends on how those electrons are distributed in energy. In a dense plasma, collisions tend to push particles toward thermal equilibrium. In a tenuous plasma, non-thermal tails can persist, and small pockets of accelerated particles can dominate the light. The baseline must allow for both thermal glow and sporadic high-energy outliers. Magnetic fields matter because they store and release energy. They also control how electrons spiral, how heat is transported, and how angular momentum is redistributed. In an accretion flow, magnetic fields are not passive threads, they are active agents. Differential rotation stretches field lines, amplifying them like taffy pulled between spinning hands. The magneto-rotational instability, MRI, turns that stretching into turbulence, enabling angular momentum transport. Without it, the gas would orbit politely and never fall in, and the black hole would remain dark. Turbulence is the engine that drives accretion. It mixes the plasma, amplifies fields, and creates intermittent structures that can brighten and fade. Turbulence also creates a kind of statistical personality. The flow does not have a single state, it has a distribution of states, and the brightness is a time series rather than a constant. That matters for imaging because an interferometer does not take a snapshot in an instant. It accumulates information over minutes and hours, while the source itself is evolving. From this baseline, we can predict what telescopes should measure. We expect emissions shaped by relativistic gravity and by magnetized plasma physics. At radio and millimeter wavelengths, the dominant mechanism is synchrotron radiation. Electrons spiraling in magnetic fields emit strongly, especially when they are hot. Synchrotron radiation has a distinctive character because it is tied to both particle energy and magnetic field strength. A single electron emits a broad spectrum as it curves, but a population of electrons produces a smoother continuum. The brightness and spectral slope encode the energy distribution of those electrons. In plain terms, the radio glow is a map of where charged particles are being whipped around by magnetic fields. The millimeter band is special for Sagittarius A. It can pierce much of the interstellar absorption and can approach the horizon scale in angular resolution. It is also special because of optical depth. At longer radio wavelengths, the plasma can become opaque, and we see only a photosphere-like surface. At millimeter wavelengths, the flow becomes more transparent, and the emission comes from closer to the black hole. The band is a compromise between clarity and practicality, because Earth's atmosphere absorbs strongly at many frequencies. The EHT lives in the narrow window where the sky, the plasma, and the technology all cooperate. In the infrared, we often see flares from a smaller population of higher energy electrons. These can be thermal tails or non-thermal particles accelerated in bursts. Infrared flares are dramatic because they rise above the steady background. They hint that the electron distribution is not always calm and that energy can be injected suddenly. The flare-light curves can be sharp, with substructure that suggests compact regions. When the infrared brightens, the question becomes immediate. What changed in the plasma, and where did the extra energy come from? In X-rays, Emission can arise from very energetic electrons through synchrotron or inverse Compton processes. X-rays signal that particle acceleration has crossed a threshold. Inverse Compton scattering is a kind of energy exchange, where fast electrons kick low-energy photons up to higher energies. In the galactic center, those seed photons can be synchrotron photons from the same plasma, scattered into the X-ray band. Alternatively, electrons can be accelerated enough that synchrotron emission itself reaches X-ray energies, which requires extreme conditions. Either way, X-rays are a warning light, indicating that the plasma has briefly entered a more violent regime. The spectrum is not one simple curve. It is a combination of thermal and non-thermal components that can change with time and with radius. Different radii contribute different temperatures, densities, and magnetic field strengths. Close in, gravity compresses and heats, and the relativistic effects intensify. Farther out, the flow is cooler and slower, and the emission shifts. The observed spectrum is an integrated story, blended along the line of sight and filtered by absorption and scattering. To decode it, we need both physics and geometry. Radiative transfer adds another layer because the plasma can absorb its own light. Optical depth changes with frequency, so different bands sample different depths. At some frequencies, we see the outer flow, while at others we see closer in. This is why multi-wavelength timing matters for building a consistent model. If an infrared flare is followed by an X-ray flare, we ask whether the same electrons did both jobs. If a millimeter brightening lags behind, we ask whether the emitting region expanded or cooled. Timing becomes a ruler for size, because light travel time and orbital time set limits. In a region only light minutes across, even a small delay can reveal the structure. Now we introduce the feature that makes black holes imageable. Strong gravity creates a shadow, a dark depression in brightness against the glowing background. The word shadow is carefully chosen because it implies a silhouette cast by geometry rather than a physical surface. In a normal shadow, an object blocks light from behind it. Here, space-time itself removes photon paths, creating a deficit in rays that can reach the observer. The result is a central dim region, surrounded by a brighter ring where lensing concentrates light. The shadow is not the horizon itself, it is the lensed imprint of photon trajectories that are captured, leaving fewer rays to reach the observer. In fact, the shadow is larger than the horizon's apparent size because lensing enlarges the capture cross-section. Photons that would have missed the horizon in flat space can be bent inward and swallowed. The boundary of the shadow corresponds to critical trajectories, those that asymptotically approach unstable photon orbits. This is why the shadow's diameter is a robust geometric prediction, tied closely to mass and distance. Photons that pass near the black hole can loop around before escaping. Those near circular paths create a brightened ring-like feature in images. Imagine a ray skimming the edge of capture, circling once, then escaping toward Earth. Now imagine another ray circling twice, and another circling 3 times, each one delayed and dimmer. In an ideal world, with perfect resolution, these multiple loops would stack into an extremely narrow feature. In the real world, the plasma emits across a range of radii, and the ring becomes thicker, textured, and time variable. This is the photon ring, produced by extreme lensing and repeated orbits. It is narrow in idealized models, though real plasma broadens and blurs it. The ring and shadow depend mainly on mass, spin, and viewing angle. They are less sensitive to the messy details of turbulence than raw brightness patterns. That is why horizon-scale imaging is powerful. It targets geometry that general relativity predicts robustly, even when the plasma is complicated. But robust does not mean trivial. The plasma can still bias what we infer because emission is not uniform and the ring can be brighter on one side. Relativistic beaming makes approaching material look brighter and receding material dimmer. Even if the shadow size is fixed, the apparent crescent can shift with viewing angle and flow orientation. The baseline expectation therefore includes asymmetry, not a perfect donut. The Event Horizon Telescope uses very long baseline interferometry at millimeter wavelengths. It links dishes across Earth to reach micro-arcsecond resolution. VLBI works by turning Earth into a virtual aperture, but it does so in pieces. Each pair of telescopes measures a spatial frequency, a Fourier component of the image. Over time, as Earth rotates, the baselines sweep out more coverage. The technique is powerful, yet it is also fragile because it depends on precise timing, stable instrumentation, and careful calibration. The raw data are not pictures. They are interference patterns that must be reconstructed. For Sagittarius A, that resolution is enough to probe the horizon scale. The target is small, but the predicted shadow size is within reach. The distance to the galactic center is about 8 kiloparsecs, close enough that the black hole's apparent size is surprisingly large. Yet, large here still means tens of micro-arcseconds, like reading a date on a coin from the other side of the moon. To reach that scale, we need millimeter wavelengths and continental baselines. We also need the atmosphere to cooperate, because water vapor can scramble the phase of the signal. Yet Sagittarius A is also variable on short timescales. Imaging requires combining data over time, so variability can masquerade as structure. This is a special challenge for Sagittarius A compared with the black hole in M87. M87's black hole is far more massive, so its characteristic timescales are longer, and the source is more stable over an observing night. Sagittarius A changes on the same timescale that the EHT builds its image. The data are like a long exposure of a moving subject, where motion blur can look like a feature. The baseline expectation is therefore statistical. We expect a shadow and ring consistent with the mass, plus fluctuating brightness from a turbulent flow. Instead of one true image, we expect a family of images, each plausible within the same physical model. The question becomes whether the geometry persists across that family. Does the dark depression remain in the same size range, even as the bright regions shift? If it does, that is a victory for the baseline. If it does not, we must ask whether the culprit is physics or measurement. Polarization adds a second channel of information that brightness alone cannot provide. Synchrotron emission is naturally polarized when magnetic fields are ordered. Polarization is not just a decorative overlay, it is a tracer of magnetic structure. The electric field vector of the radiation carries information about the field direction in the emitting region. In synchrotron emission, the polarization can be high in principle, but it is easily reduced by disorder. That sensitivity makes polarization a stringent test, because it punishes sloppy models and rewards coherent geometry. The polarization fraction and angle encode the projected magnetic field geometry. They also encode relativistic effects that rotate and mix polarization near the hole. Close to the black hole, light does not simply travel, it is parallel transported through curved spacetime. The polarization vector can rotate as it moves along a bent path, and different rays can arrive with different rotations. This gravitationally induced rotation can mimic or mask plasma effects. The baseline must therefore include both magnetized emission physics and relativistic propagation, because the observed polarization is the product of both. If the field is tangled on small scales, polarization can cancel out. If the field is coherent, polarization can remain strong and structured. A tangled field is like a crowd shouting different directions. The net message averages towards silence. A coherent field is like a choir, where alignment produces a clear signal. In images, coherent fields can produce polarization patterns that trace loops, spirals, or radial structures. Those patterns can hint at whether the flow is dominated by turbulence, by shear, or by a large-scale magnetic flux threading the inner region. Between Sagittarius A and Earth, polarized light passes through magnetized plasma. This causes Faraday rotation, which twists the polarization angle with wavelength. Faraday rotation is a propagation effect, not an emission effect, and it depends strongly on wavelength. The rotation angle scales roughly with the square of the wavelength, so small changes in frequency can produce large changes in angle at longer wavelengths. The amount of rotation depends on the integral of electron density and magnetic field along the line of sight. In plain language, the galaxy itself can twist the signal like a dial. Strong Faraday rotation can also depolarize the signal across a finite bandwidth. That depolarization depends on electron density and magnetic field along the path. If the polarization angle rotates significantly within a single observing channel, the measured polarization can average down. The result is not necessarily a lack of intrinsic polarization, but a smearing imposed by the intervening plasma. This is why high-frequency, narrow-band, well-calibrated observations matter so much. To interpret the polarization, we must separate what happened at the source from what happened on the way. Faraday effects can occur in the accretion flow itself and in intervening material. Measuring rotation helps constrain the density and field strength near the source. A measured rotation measure is more than a number. It is a constraint on the accretion rate and magnetic environment. If the rotation is too high, it implies dense plasma or strong fields, which can conflict with the observed dimness. If it is too low, it can imply a more tenuous or differently structured flow. The baseline uses these constraints like guardrails, limiting which models can survive. Polarization variability has a clear diagnostic meaning. Stable polarization suggests a persistent field geometry, while rapid swings suggest evolving structures or viewing changes. A stable polarization angle over many hours would be surprising in a purely turbulent picture. It would hint that, beneath the flicker, there is an organizing structure, perhaps a preferred axis or a persistent magnetic loop. Rapid swings, by contrast, could indicate reconnection events, orbiting features, or changes in optical depth. The baseline expects some variability, but it also asks how that variability is distributed. A key baseline question is whether polarization changes are stochastic or coherent. Coherence would imply an organized driver in a region expected to be turbulent. Variability is expected even in standard models. Turbulence creates flicker noise, with fluctuations across a range of timescales and amplitudes. In many accreting systems, variability follows a power spectrum, with more power at longer timescales and a cascade toward shorter ones. That red noise behavior is a fingerprint of turbulent processes. It means that patterns can appear briefly coherent by chance, simply because random fluctuations can align. The baseline therefore demands caution before declaring a periodic signal, especially when the data are noisy and sparse. Magnetic reconnection can create flares by rapidly converting magnetic energy into particle energy. That can produce infrared and X-ray spikes with correlated timing. Reconnection is the plasma equivalent of a snapped rubber band. Field lines that were stretched and stressed can rearrange into a lower energy configuration, releasing energy into heat and particle acceleration. In the Sun, reconnection powers solar flares. Near Sagittarius A, it can occur in a far more extreme environment, where the plasma is relativistic and the magnetic energy density can rival the particle energy density. The baseline expects reconnection to be intermittent, localized, and capable of producing sharp, bright events. Another proposed source of variability is orbiting hotspots. A localized bright region can circle near the innermost stable circular orbit and modulate emission. A hotspot is a useful mental model, even if reality is more complex. It could be a blob of plasma heated by reconnection, a shock, or a transient compression. As it orbits, lensing can magnify it at certain phases, and Doppler beaming can brighten it when it moves toward us. The result can be a quasi-periodic modulation, not because the system is a clock, but because orbital motion is a repeating geometry. The ISCO is a general relativistic boundary for stable circular orbits. Inside it, material plunges inward quickly, changing the character of variability. In Newtonian gravity, circular orbits can exist arbitrarily close to a point mass. In general relativity, stability ends at the ISCO, and inside it, the effective potential changes. Matter can still orbit briefly, but it cannot remain on a stable circular path. This boundary matters because it sets a natural scale for the fastest persistent variability. It also sets a scale for where the emission might become more chaotic and more strongly lensed. Timescales scale with black hole mass, which sets the gravitational radius and orbital periods. For Sagittarius A, near ISCO periods are minutes to tens of minutes. That is a human timescale, which is part of the mystery. We can watch the galactic center change in real time, not over geological epochs. A feature can brighten, orbit, and fade within a coffee break, and that immediacy tempts us to see patterns. The baseline reminds us that fast does not mean simple. It means we are watching a turbulent system at close range. Longer timescales of hours can arise from larger radii, slower inflow, and evolving magnetic structures. The baseline expects a hierarchy, not a single clock. Quasi-periodic signals are possible but fragile. In a turbulent flow, coherent periodicity should drift, broaden, or disappear unless a stable mechanism sustains it. This is where skepticism becomes part of the blueprint. A periodic-looking signal can arise from an orbiting feature, but it can also arise from chance alignments in red noise. A true quasi-periodic oscillation would need to persist across observing campaigns and appear in multiple bands. Even then, it must survive the distortions of scattering and the biases of irregular sampling. Spin is the parameter that can add structure without adding matter. In the Kerr solution, a spinning black hole drags spacetime around with it. The Kerr solution is one of the triumphs of 20th century relativity, describing a rotating black hole with just mass and spin. Frame dragging is not a small correction near the horizon. It can dominate the motion. Space-time itself is pulled into rotation, and anything that tries to remain stationary is forced to move. This is not like wind pushing an object. It is geometry redefining what stationary means. Frame dragging affects orbital motion and can shift the ISCO inward for prograde orbits. That changes the fastest possible periods and the hottest regions. If the accretion flow rotates in the same direction as the black hole, stable orbits can exist closer in and the orbital frequency increases. If it rotates against the spin, the ISCO moves outward and the inner flow is less tightly bound. These differences can imprint themselves on variability timescales and on the brightness distribution. The baseline therefore keeps spin in view, even if it is hard to measure directly. Spin also affects lensing and the shape of the shadow slightly. More importantly, it can influence magnetic field dynamics and the potential for jet launching. The shadow shape is only modestly distorted for realistic spins and viewing angles, which is why the shadow is such a clean test of mass. But spin can matter greatly for dynamics because it can help organize magnetic fields and enable energy extraction. The idea that rotational energy can be tapped is not speculative hand-waving. It is a consequence of the Kerr geometry and electromagnetic fields. Whether Sagittarius A uses that option is an observational question. Jets are not guaranteed for Sagittarius A, but the theory connects spin and magnetic flux. A strong, ordered field near the horizon can tap rotational energy. This raises a baseline expectation about magnetic geometry. If the inner flow accumulates large-scale flux, polarization could show persistent alignment. A persistent alignment would be a kind of compass needle, pointing to an underlying axis. It would suggest that, despite turbulence, the inner region maintains a preferred direction. That could happen if magnetic flux accumulates and resists being shredded, or if the flow geometry is constrained by rotation. Such a signature would be subtle, because it must survive Faraday rotation and observational noise. But Sagittarius A is underfed and may not sustain a stable, magnetically arrested state. The baseline remains uncertain, which is why polarization is so valuable. In an underfed system, the supply of magnetic flux and matter is intermittent. The inner flow might flirt with an organized state and then relax back into disorder. That ambiguity is not a flaw, it is an opportunity, because it means the data can decide. The baseline is not a single prediction, it is a constrained range of behaviors. Every prediction must be filtered through observational reality. The galactic center is distant, crowded, and viewed through a turbulent interstellar medium. The line of sight passes through the disk of the Milky Way, where ionized gas is patchy and magnetized. The region is also crowded with stars, dust, and complex structures, which complicate measurements at many wavelengths. Even when the black hole's emission is isolated, the path it takes to us is not empty. The baseline must include the galaxy as part of the instrument. At radio wavelengths, interstellar electrons scatter the waves and blur the image. Scattering broadens structure and can impose an apparent size unrelated to the source. Scattering is like viewing a distant streetlight through frosted glass. Small-scale density fluctuations in the ionized medium act like a random lens, spreading the image and introducing refractive substructure. The effect is stronger at longer wavelengths, which is why early radio images could not see the horizon scale. Even at millimeter wavelengths, scattering is reduced but not eliminated, and its imprint must be modeled. Scattering is frequency-dependent, so higher frequencies reduce the blur. That is another reason millimeter observations are essential for horizon-scale work. Calibration is another limiting factor, especially for polarization. Small instrumental errors can create false polarization signals or erase real ones. Polarization calibration is unforgiving because it requires separating tiny differences between channels and antennas. Leakage between polarization states can mimic a real signal, and phase errors can rotate the measured angle. The EHT's strength is that it combines many stations, but that also multiplies the calibration challenge. The baseline expectation therefore includes an awareness of what the instrument can accidentally invent. Interferometric imaging is also sparse by nature. The EHT samples only certain spatial frequencies, so reconstruction depends on algorithms and assumptions. The image is not directly measured, it is inferred. Different algorithms can prefer smoothness, compactness, or other priors, and those preferences can shape the result. This is why the EHT uses multiple imaging pipelines and cross-checks. A feature that survives across methods is more likely to be real, because it is less dependent on a particular assumption. For Sagittarius A, variability adds a further complication. The source changes during the observation, so the data are not strictly consistent with a static image. To address this, analysts can use time-resolved approaches or model the source as a stochastic process. They can also test whether the inferred shadow size is stable, even as the brightness pattern evolves. The baseline does not demand a perfectly frozen ring, it demands a persistent geometric scale. That distinction is crucial, because it tells us what kind of agreement counts as success. This is why multi-instrument confirmation is critical. If a feature appears in independent datasets and methods, it is less likely to be an artifact. Independent confirmation can come from different frequencies, different arrays, or different epochs. It can also come from consistency with constraints like mass measurements from stellar orbits. The galactic center has a unique advantage here, because the mass of Sagittarius A is not guessed from luminosity. It is measured from the dance of stars, tracked over years, which anchors the geometric predictions. The baseline model therefore includes a disciplined skepticism. We expect a lensed shadow and ring, turbulent brightness, polarized synchrotron emission, and stochastic variability. We also expect that some apparent patterns will be produced by scattering, sampling, and reconstruction. The baseline must separate robust geometry from fragile details. When observers claim an anomaly, the first test is whether it violates the baseline in a way that survives these filters. The second test is whether it repeats. A single surprising image can be a mirage, born from noise, calibration drift, or an unlucky moment of variability. A repeating discrepancy is harder to dismiss, because it suggests a persistent physical cause. Even then, the anomaly must be defined carefully, in terms of measurable quantities like ring diameter, asymmetry, polarization structure, or timing correlations. The baseline is the grammar, and the anomaly is a sentence that does not pass. The goal of this chapter is a mental model, not a final answer. General relativity supplies the geometry, plasma physics supplies the glow, and instruments supply constraints. With that blueprint in place, the anomaly becomes legible. We can ask whether the data match the expected grammar of lensing, polarization, and variability. Now we follow the data rather than the equations. What the telescopes recorded is where the story begins to diverge from expectation. In the next step, the abstract picture becomes a set of measurements, visibilities, closure phases, polarization fractions, and time series. The question is no longer, what should a black hole do? But what did this one do on these nights through this intervening galaxy? And that is where mystery enters, not as decoration, but as a scientific tension. With the blueprint in place, the anomaly becomes a measurement problem, because theory only matters if nature repeats it under scrutiny. The question shifts from equations to telemetry, from what should happen to what returns in the data. In practice, that means asking whether a pattern survives the messy realities of calibration, weather, and imperfect sampling. Sagittarius A star is monitored the way storms are monitored, with long baselines, many sensors, and patience for false alarms. The source is faint, fast, and buried behind a complicated line of sight, where dust dims the light and plasma distorts radio waves. Even before the black hole enters the story, the Milky Way's center acts like a filter, selective, turbulent, and never fully still. The first data stream is the light curve, brightness plotted against time, and it is deceptively simple. On a screen, it looks like jitter, a restless baseline with spikes that may or may not matter. Only after it is folded, filtered, and compared across nights does structure begin to separate from noise. Sampling cadence matters here, because gaps can manufacture rhythms that were never present. In the near-infrared, the baseline glow is low, then flares rise sharply above it, as if a hidden switch were thrown. Each flare is a short-lived experiment run by nature in the inner flow, where gravity is strong and magnetic fields are stressed. The rise can be steep, the peak brief, and the decay long enough to tempt pattern-seeking eyes. Visually, the flare looks like a spark in a dark furnace, brightening and fading, while the background remains stubbornly dim. Observers track start times, rise times, peak flux, and decay slopes, because timing is the first clue to mechanism. They also track substructure, because bumps inside a flare can carry orbital timing, shock signatures, or lensing echoes. A flare is not always one smooth hill, and the smaller ripples can be the most diagnostic. In a turbulent plasma, those ripples can also be the most treacherous, because randomness naturally produces clusters and pauses. A second stream is the spectrum, brightness plotted against wavelength, and it is where the flare's physics begins to speak plainly. Spectra tell whether electrons are thermal, non-thermal, or switching between regimes mid-flare, which is a polite way of asking how violent the acceleration was. A thermal spectrum suggests a hot but orderly population, while a non-thermal tail suggests a minority of particles pushed to extreme energies. In synchrotron emission, the slope of the spectrum encodes the electron energy distribution. Technical, yes, but also direct, because it is the plasma writing its own autobiography. A third stream is polarization, both fraction and angle, and it is the most sensitive to geometry. Polarization is a compass for magnetic structure, and it is also a stress test for calibration, because tiny instrumental leaks can masquerade as cosmic twists. In the infrared, polarization can rise during flares, implying a more ordered magnetic field in the emitting region. The angle can rotate, and when it does, it suggests either a changing field direction or a changing viewing geometry. For a narrator, it is an invisible arrow that suddenly becomes visible, pointing, turning, and sometimes spinning. A fourth stream comes from interferometry, where the telescope measures visibilities rather than taking a straightforward picture. Visibilities are Fourier samples of structure, not images, and they must be assembled carefully across baselines and time. Each pair of telescopes measures a complex number, an amplitude and a phase that corresponds to a specific spatial frequency. The longer the baseline, the finer the detail it probes. but the more fragile the measurement becomes. In visuals, the Earth itself becomes part of the instrument, rotating to sweep those baselines through different orientations. Across these streams, the anomaly is not introduced as a single dramatic spike that any viewer could spot instantly. It is introduced as a recurring pattern that survives different reductions and different instruments, which is the only kind worth fearing. A one-off event can be a glitch, a weather artifact, or a statistical fluke. A pattern that returns, subtly but consistently, demands a deeper accounting. The investigation begins with the simplest claim, because extraordinary interpretations should be the last resort. Are we seeing a real clock near the horizon, or are we seeing red noise dressed up as rhythm? Red noise is not just messy data. It is a process with memory, where fluctuations at one time influence the next. In such a process, apparent periodic peaks can appear naturally, especially when the time series is short. Near-infrared monitoring provides the most immediate timing because the flares are sharp and the cadence can be fast. Gravity, on the VLTI, resolves the galactic center with interferometric astrometry, not direct imaging, and that distinction matters. It does not produce a conventional photograph of a moving blob. Instead, it uses interference fringes to infer where the light's centroid sits, moment by moment, on the sky. Gravity measures fringe phases that translate into centroid positions, and those phases are exquisitely sensitive to path length. In favorable flares, it tracks motion at micro-arcsecond scales over minutes, a precision that feels almost absurd. A micro-arcsecond is like resolving a coin on the moon from Earth, except the coin is flickering and the atmosphere is boiling. The instrument's internal metrology, lasers, fiber paths, and delay lines, has to behave like a ruler that never flexes. That precision matters because the gravitational radius of Sagittarius A star subtends micro-arcseconds at our distance. The black hole's mass is about 4 million suns, and the scale of its horizon is measured in light seconds. On the sky, that becomes a tiny angle, and yet it is not beyond reach. A centroid shift can correspond to motion near the innermost flow, where orbital periods are counted in minutes. Some campaigns report centroid tracks that look orbit-like, and that is where the story turns. The motion appears to loop, sometimes with a preferred sense of rotation, as if a bright region is circling the black hole. The loop is not always a perfect circle, and it is not always closed, but it is coherent enough to be unsettling. In visuals, the centroid becomes a glowing dot, tracing a lopsided ring, hovering at the edge of an unseen abyss. The expected timescale is set by the innermost stable circular orbit, the ISCO, which depends on spin and sets a natural clock. For this mass, the period is minutes to tens of minutes, and that range is not arbitrary. It comes from general relativity's prediction that stable orbits end near the horizon, where space-time curvature steepens. A hotspot near that radius can modulate both flux and position, because Doppler boosting brightens the approaching side and dimming follows as it recedes. In standard models, the loop should not be too clean, because the environment is not a frictionless track. Turbulence shears blobs, differential rotation stretches them into arcs, and magnetic stresses can shred coherence quickly. Gravitational lensing duplicates images, and the centroid path should wander and decohere as multiple lensed components trade dominance. Even if a hotspot forms, it should be short-lived, an ember in a storm. The anomaly is framed as coherence that lasts longer than expected, and that framing is careful for a reason. The centroid motion sometimes repeats a quasi-periodic cadence across multiple flares, as if the system revisits the same configuration. Quasi-periodic does not mean perfectly periodic, and the drift matters. Still, the recurrence hints at an underlying mechanism that can keep time, even while plasma churns. In some events, the inferred speed looks too high for a simple orbit, and the phrase superluminal enters the conversation. It resembles superluminal motion, which in this context can be a lensing illusion rather than a violation of relativity. Apparent faster-than-light motion is a known effect in astrophysics. often produced by geometry and light travel time delays. Near a black hole, lensing adds an additional trick because the path of light itself is bent into new routes. Extreme lensing can shift the apparent centroid rapidly when a bright patch crosses an amplification region, where small changes produce large apparent motion. The sky position can jump even if plasma moves subluminally, because the brightest image can switch from one lensed path to another. The effect is like watching a reflection move on rippling water, where the reflection can leap through the source does not. The black hole's photon ring, predicted by relativity, is part of this optical machinery, trapping light briefly before releasing it toward us. Yet the reported jumps have a twist that keeps the anomaly alive. Their timing and direction do not always match the simplest orbiting hotspot templates, even when lensing is included. A basic model expects certain phase relationships between flux peaks, centroid position, and polarization angle. When those relationships shifts, the suspicion shifts from a blob on a track to something more structured or more deceptive. Researchers test whether the loops are artifacts of phase referencing, because interferometry can be unforgiving. They check metrology, fiber delays, baseline solutions, and atmospheric piston corrections, hunting for subtle biases. A small, unmodeled delay can create a false drift, and a drift can look like motion. They also test whether the loops correlate with baseline orientation, which would hint at an instrumental signature rather than a celestial one. They also test whether nearby stars contaminate the centroid, because the galactic center is crowded with bright sources. A changing background can bias astrometry, especially when the flare is faint or the seeing is variable. Confusion is not a theoretical nuisance here, it is a daily operational constraint. In visuals, the flare sits in a glittering field, and the question becomes whether the dot is moving or the background is tugging it. The next check is spectral behavior during the same flares, because a real moving emitter should cool and evolve. If the centroid motion is real, the spectrum should evolve consistently with acceleration and losses, even if the geometry complicates the view. Synchrotron cooling has a characteristic timescale that depends on magnetic field strength and electron energy. If electrons are pushed to higher energies, the spectrum hardens. As they cool, it softens. Some flares show spectral hardening as they rise, then softening as they fade, and that pattern is physically legible. It fits particle injection followed by synchrotron cooling, where a burst of acceleration populates high-energy electrons that then radiate away their energy. The cooling is faster at higher frequencies, so the spectrum can steepen with time. The flare becomes a stopwatch for microphysics, measuring how quickly the plasma can lose energy in a strong field. Other flares show timing structure without the expected spectral evolution, and that mismatch is not easy to ignore. If the brightness oscillates, but the spectrum stays stubbornly similar, the driver may be geometric rather than energetic. Doppler boosting can modulate flux without changing the intrinsic electron distribution, and lensing can brighten without heating. The anomaly, in this view, is a choreography of light paths and viewing angles, not a series of explosions. Polarization adds a second layer of motion, because the angle can rotate as the field geometry changes or as the emitting region moves. In a simple hotspot, polarization swings track orbital phase, producing a smooth rotation as the spot circles. The polarization fraction can rise when the field is ordered and fall when turbulence dominates. When the angle rotates, it is as if the magnetic field is drawing circles in the air. Several datasets show rapid polarization angle swings during flares, and the swings can be smooth and large. They look as if a coherent field is rotating in view, or as if the emitting region is sampling different field orientations along its path. In a strong gravity environment, even the polarization vector can be parallel transported along bent light rays, adding a relativistic twist. That means the observed angle is not just local magnetism, but magnetism filtered through curved spacetime. The anomaly appears when the swings are too fast or too repeatable, because speed implies either compactness or extreme ordering. The implied magnetic geometry seems to flip on timescales that strain standard reconnection pictures, which often predict messy, intermittent structures. Reconnection can be rapid, but it tends to produce a cascade of plasmoids and turbulence. A clean, repeating rotation suggests a more stable engine, or a preferred topology that reasserts itself. Before claiming new physics, teams interrogate the instrument, because polarization calibration is unforgiving. Leakage between polarization states can create false rotations, and small errors can accumulate into dramatic-looking swings. They compare independent calibrators, swap reduction pipelines, and test for frequency-dependent leakage. They also check whether angle swings correlate with weather and elevation, because the atmosphere and optics can imprint subtle systematics. They then model Faraday rotation along the line of sight, because magnetized plasma can rotate the polarization angle. A changing rotation measure could mimic intrinsic swings if the intervening plasma fluctuates on the right timescale. Faraday rotation scales strongly with wavelength, which makes it a powerful diagnostic. If the angle changes are propagation-induced, they should grow dramatically at longer wavelengths. At near-infrared wavelengths, Faraday rotation is small, so large swings are harder to blame on propagation. That pushes suspicion back toward the source, toward the inner accretion flow itself. The infrared, in this sense, is a cleaner window, though not a perfect one. Dust still dims and reddens, but it does not usually spin polarization on minute scales. The story then widens to millimeter wavelengths, where the Event Horizon Telescope targets horizon-scale structure. Here the data are not light curves first, but visibilities and closure quantities, the raw language of interferometry. The EHT is not one telescope, but a planet-sized array stitched together by atomic clocks and careful correlation. Its resolution is measured in tens of micro-arc seconds, designed to match the shadow scale predicted by relativity. Sagittarius A star is harder than M87 star for one central reason, and it is not distance or brightness alone. The source evolves during the hours needed to synthesize an image with Earth rotation, which is the very trick that gives the array its power. In M87 asterisk, the black hole is far more massive, so intrinsic variability is slower, and the sky holds still long enough to be imaged. For Sagittarius A asterisk, the same physical processes run on human timescales, and the target refuses to pose. That means a static imaging assumption can smear structure in subtle ways that look like physics. A moving brightness pattern can masquerade as a thicker ring, a shifted crescent, or spurious asymmetry. Even if the underlying ring is stable, the bright regions on it can drift, brighten, and fade. The image then becomes a time average of a living system, and the question becomes, what survives averaging? The EHT counters this with algorithmic diversity and consistency tests, because no single reconstruction method is trusted alone. Multiple pipelines reconstruct images under different priors and compare robust features, looking for convergence. Some methods favor smoothness, others favor sparsity, and each can invent artifacts if pushed. Agreement across methods is treated like a form of triangulation, not proof, but pressure. They also use observables that resist calibration errors, because station-based mistakes are inevitable at this precision. Closure phase and closure amplitude cancel station-based phase and gain terms, leaving combinations that depend mostly on source structure. Closure phase tests asymmetry in the brightness distribution, while closure amplitude tests relative structure with reduced dependence on absolute calibration. These quantities are not immune to every problem, but they are harder to fool with a single bad antenna. If a feature appears in closure quantities, it is less likely to be a single-station artifact, and that is why they are central to the narrative. It still could be a modeling bias, or an effect of variability interacting with sparse sampling. Yet it becomes harder to dismiss because it is encoded in relationships among multiple stations. In visuals, the closure phase is like a chord that stays in tune even when individual instruments drift. EHT reconstructions of Sagittarius A star converge on a ring-like structure, and that convergence is itself a triumph. The ring diameter is consistent with expectations from mass and distance constraints, which ties the image back to independent measurements of the black hole's mass. Historically, That matters because Sagittarius A star was identified as a compact radio source decades ago, and its mass was pinned down through stellar orbits. The image, then, is not a standalone picture, but a cross-validated result, linking radio interferometry to infrared astrometry. Within that success, the anomaly is introduced as a subtle inconsistency rather than a contradiction. Certain epochs show a recurring substructure pattern that aligns across reconstructions, as if the brightness distribution prefers certain modes. The pattern is not a stable, bright knot that sits in one place for hours. It is a repeatable modulation in visibility phases that suggests a preferred geometry, returning more often than chance would suggest. One framing is unexpectedly coherent quasi-periodicity during the observing window, where the source seems to revisit a similar configuration. Another framing is polarization behavior that implies a field topology switching too quickly, as if magnetic order is reorganizing on the fly. A third framing is apparent centroid shifts that are too organized to be pure turbulence, especially when compared to simulations. Each line alone is ambiguous, but their overlap becomes the pressure point. The chapter treats this overlap as a triangulation problem because no single dataset can carry the burden. Timing, structure, polarization, and motion must be consistent with one physical narrative, or the anomaly dissolves. If the centroid loops are real, they should connect to polarization swings and to millimeter structure in plausible ways. If the EHT sees preferred geometry, it should not contradict the infrared's timing constraints. The goal is coherence across methods, not drama in any one plot. Cross-checking across wavelengths becomes the next test, because different bands sample different electron energies and optical depths. Infrared flares sometimes coincide with X-ray flares, and sometimes they do not, and that split is informative. When IR and X-ray peaks coincide, it suggests a shared acceleration episode, where electrons are pushed to energies high enough to radiate in both bands. Magnetic reconnection can inject non-thermal electrons that radiate synchrotron in IR and either synchrotron or inverse Compton in X-rays, depending on conditions. When IR flares lack X-ray counterparts, it suggests a lower maximum electron energy, a weaker magnetic field, or a different emission channel. It can also imply geometric modulation without extra heating, where beaming and lensing change what we see. In that case, the IR is bright because of orientation, while the X-ray remains quiet because no new high-energy tail was created. The absence becomes a clue, not a failure. The anomaly becomes sharper in the mixed cases, where the timing signature appears without the expected high-energy response. Some nights show the cadence, the centroid behavior, or the polarization swing, yet the X-ray instruments see no corresponding flare. That is uncomfortable for models that tie the pattern to violent acceleration. It suggests the pattern might be a geometric clock riding on top of variable particle physics. Researchers then ask whether the X-ray instrument missed a short spike, because X-ray observing is often interrupted by Earth occultations and scheduling. They examine exposure gaps, pile-up corrections, background subtraction, and detection thresholds, looking for ways a flare could hide. They also test time binning, because a flare can vanish if averaged over too long an interval. The analysis becomes forensic, because a non-detection can be as fragile as a detection. They also ask whether absorption changed, because the galactic center is embedded in gas and dust that can attenuate soft X-rays. Variable absorption could suppress a flare in one band while leaving another relatively untouched. Yet absorption changes on minute timescales are difficult to arrange without an implausibly compact, rapidly moving absorber. Even after these checks, the mismatch persists in some events, and that persistence matters. The line of sight itself is treated as a suspect, especially at radio wavelengths, where propagation effects are severe. Interstellar scattering blurs radio images and can imprint refractive substructure that changes with time, like heat shimmer on a desert road. The scattering is produced by electron density fluctuations in the ionized interstellar medium. It acts like a random lens, broadening the apparent source and adding speckle-like distortions. Scattering is frequency-dependent, and its signature scales predictably with wavelength, which makes it testable. Observations at multiple frequencies can separate intrinsic structure from scattering artifacts, because intrinsic features do not follow the same scaling law. At longer wavelengths, the scattering kernel dominates, and the source looks larger and smoother. At shorter millimeter wavelengths, intrinsic structure emerges, and the kernel weakens, allowing the horizon-scale ring to show through. Teams model the scattering screen using decades of radio data, including measurements of angular broadening and refractive noise. They test whether the observed visibilities could be produced by a static source convolved with scattering, plus realistic refractive fluctuations. They also simulate refractive noise, which can create apparent substructure and shift centroids slightly, especially on certain baselines. The question is whether the anomaly could be a mirage produced by the galaxy itself. The anomaly is presented as surviving these scattering models, which is a careful claim rather than a sweeping one. The pattern appears at frequencies where scattering should be too weak to create it alone, and it appears in ways that do not match expected refractive statistics. That does not eliminate scattering as a contributor, but it demotes it as the primary author. The source, not the screen, remains the leading suspect. Dust is another suspect, especially for infrared, because extinction shapes what we can see. Variable extinction could modulate flux and polarization if the line of sight changes, or if local dust structures drift across the beam. Yet extinction changes are slow compared with minute-scale flare structure, because dust clouds do not rearrange that quickly. Dust can set the baseline and the color, but it cannot easily write a rapid quasi-periodic code. Intervening plasma is also tested through dispersion and rotation measures because a fluctuating medium should leave correlated signatures. If the medium were responsible, changes in polarization rotation should track changes in other propagation indicators. The data do show a complex medium, but not one that tracks the anomaly's timing with the required precision. That weakens the case for a purely environmental origin, though it never fully removes the environment from the story. Statistical rigor becomes the gatekeeper, because quasi-periodicity claims are vulnerable to self-deception. Red noise produces false peaks in power spectra, especially when the dataset is short and the sampling uneven. Analysts model the underlying noise as a power law process, fitting parameters that describe how variability power increases toward low frequencies. They generate Monte Carlo light curves with the same sampling and noise properties, then process them through the same analysis pipeline. They then ask how often a random process produces a peak as strong as the observed one, and the answer is a distribution, not a single number. Significance is reported with uncertainty, because the noise model itself has uncertainty. They also correct for trials, because searching many frequencies inflates false positives, and a peak that looks dramatic can become ordinary once the search is accounted for. In a documentary, this is where excitement meets discipline, and discipline usually wins. The chapter emphasizes that one dramatic flare is not enough, because nature can stage convincing coincidences. A real quasi-periodic oscillation must recur across independent datasets and survive changes in observing cadence, instrument configuration, and reduction choices. It should appear in multiple flares, not just the brightest one. It should persist when the analyst is not allowed to choose the window that makes it look best. The standard is harsh because the claim is seductive. In the gravity data, the centroid loops are tested against random walk models and against simulated turbulence. Analysts compare loop closure, curvature, and phase coherence to null hypotheses, asking whether the observed tracks are too organized to be accidental. They also examine whether the loop's sense of rotation is consistent across events, because a consistent handedness would hint at a preferred angular momentum direction. A random process can loop, but it should not prefer the same choreography repeatedly. In EHT data, substructure claims are tested against synthetic datasets because reconstruction algorithms can hallucinate features. Teams inject known source models into the pipeline and measure what the algorithms invent under realistic noise and sampling. They vary priors, regularization strengths, and time variability assumptions, watching what remains stable. If the same modulation appears across these stress tests, it becomes less likely to be an artifact. The process is slow because caution is part of the instrument. They also compare independent calibration teams because human choices can imprint patterns. If two groups using different assumptions recover the same closure behavior, confidence rises. Disagreement is equally informative because it points to fragile steps in the chain. In this sense, the anomaly is not just a feature in the sky, it is a test of the community's methods. Environmental context is then brought back in, because the galactic center is not empty and never has been. Stellar winds, gas streams, and orbiting stars feed and perturb the flow, shaping what reaches the inner region. The S-star cluster passes close, and some stars drive strong winds that collide and shock. Clumps and bow shocks concede density variations in the accretion supply, changing the fuel that the black hole receives. A passing gas cloud could in principle change the accretion rate, and the idea has historical precedent in the attention given to infalling material near Sagittarius A. A transient increase could alter flare statistics and polarization behavior for months, perhaps even changing the magnetic flux threading the inner flow. Researchers look for correlations with known orbital events, comparing flare rates and properties before and after close passages. They also search for secular trends, because a feeding change should not appear only as minute-scale timing. They also examine whether a persistent orbiting clump could mimic the anomaly by repeatedly perturbing the inner flow. A clump could modulate emission if it repeatedly triggers reconnection or compresses magnetic fields at a preferred phase. But the timescale mismatch is a problem because stellar or clump orbits are hours to years, not tens of minutes near the horizon. The inner clock is too fast to be driven directly by distant orbiters. To affect minute-scale signals, the perturbation must couple to the inner flow quickly, and that requirement is severe. It requires a mechanism that transmits changes inward without smearing them out, despite turbulence and differential rotation. Magnetic fields are a candidate for that coupling, because field lines can connect regions and transmit stresses rapidly. Large-scale flux can organize the inner region and create repeatable patterns even with variable feeding, acting like a scaffold inside the storm. Yet magnetically organized states should leave broader signatures, and the chapter leans into that tension. They should affect polarization fraction, rotation measure, and perhaps the stability of the millimeter ring, not just a narrow timing feature. The data show hints, but not a clean, single state change that would settle the matter. Instead, the anomaly appears intermittently, like a mode the system slips into, then abandons without warning. The turning point comes when the list of mundane explanations is exhausted, not because every doubt is erased, but because the same pattern keeps returning. Instrumental artifacts are reduced by independent pipelines and calibrators, and the remaining systematics are bounded. Environmental propagation effects are constrained by frequency scaling and by the small Faraday impact in infrared. Statistical flukes are weakened by recurrence, especially when the recurrence appears in different observables. What remains is subtle, repeatable, and stubbornly inconsistent with the simplest hotspot and turbulence models. It does not overthrow the baseline picture of an accreting black hole, but it bends it, forcing models to become more careful. The anomaly is not a declaration that relativity failed, and the chapter keeps skepticism active. It is a claim that the inner flow is doing something organized, something that looks like timing and geometry emerging from chaos. Still, the persistence across methods changes the tone, because multiple independent instruments rarely agree by accident. A signal that survives gravity astrometry, EHT closure quantities, and polarization checks demands a physical cause, even if that cause is still conventional. The central question returns in sharper form, and it is asked without theatrics. If this pattern is real, what engine near the horizon can keep time and geometry in a turbulent plasma? We end where the next chapter begins, with the investigation poised on a threshold. If the signal is real, we start with conventional physics pushed to extremes, then follow it toward the edge of the known. Plasma, magnetic fields, and strong gravity can create strange weather, and weather can look like intention when it repeats. The unsettling possibility is that the anomaly is the weather's fingerprint, not our instruments. And if the weather cannot explain it, the crack may be deeper, though the chapter refuses to name it too soon. The next step is to test the most conservative mechanisms first, and to watch exactly where they fail. In the static, a signal has begun to hold its shape, and the story now has to decide what kind of order can survive at the brink. The anomaly does not force exotic answers first. It forces us to exhaust conservative physics under extreme conditions. That principle sounds cautious, almost procedural, yet it is how black hole science has survived its own temptations. For decades, every surprising light curve and every strange image feature has invited speculation. The discipline's guardrail is simple. Start with gravity, plasma, and light, then push those tools until they break. Sagittarius A is dim, fast, and magnetized. Its accretion flow is a weather system where gravity sets the clock and plasma sets the texture. On screen, the center of the Milky Way is not a neat whirlpool. It is a hazy, boiling glow threaded by magnetic filaments that twist like storm fronts. The black hole itself is invisible, but its influence is everywhere, shaping matter into patterns that flicker on timescales of minutes. Sagittarius A is also underfed by galactic standards. Compared with the blazing quasars in distant galaxies, it is a low-luminosity engine. That dimness matters because it implies that most of the energy is not radiated away efficiently. Instead, much of it stays locked in the motion and heat of the plasma. We start with the simplest premise. If the signal looks organized, the organization might be an illusion created by light, time, and sampling. In astronomy, the raw reality is never handed to us directly. We reconstruct it from incomplete photons, filtered by instruments and by the interstellar medium. When the source evolves quickly, even a small observational gap can turn a drifting pattern into something that looks periodic. Accretion in this regime is not a thin, steady disk. It is a hot, radiatively inefficient flow where electrons and ions can decouple. The phrase radiatively inefficient is technical, but the idea is plain. The gas is so tenuous that it cannot easily shed its heat as light. The ions can become extremely hot, while the electrons, responsible for most of the radiation, may remain cooler, at least for a time. This two-temperature behavior is not a minor detail. It changes how the plasma emits, how it cools, and how it responds to magnetic stress. It also means that the brightest flares may come from small pockets where electrons are suddenly energized. The flow's baseline state is turbulent. Turbulence creates intermittent bright patches without any stable engine behind them. Visually, turbulence near a black hole is not like smoke in air. It is a magnetized relativistic churn where eddies stretch and fold field lines. Brightness can spike when density, temperature, and magnetic field briefly align. Then the patch dissolves, swept into the wider chaos. Yet turbulence is not featureless. MRI-driven eddies can produce correlated variability across radii, and correlated variability can mimic a weak clock. The magnetorotational instability, or MRI, is one of the great discoveries of modern accretion theory. It explains how disks transport angular momentum outward, allowing matter to drift inward. In a differentially rotating flow, weak magnetic fields behave like elastic bands. They connect faster inner fluid to slower outer fluid, and the tension destabilizes the rotation. MRI turbulence is messy, but it has structure. It can create spiral-like correlations, and it can couple regions separated by many gravitational radii. When those correlations propagate inward, they can imprint a quasi-regular rhythm on the light, even if no single object is orbiting like a metronome. To decide whether the anomaly is a clock, we first classify the flow's magnetic regime. That split is often framed as sane versus mad. These labels are shorthand, but they capture a real physical competition. How much vertical magnetic flux is dragged toward the black hole, and how strongly does that flux push back? In that contest, the accretion flow can look either loosely magnetized or magnetically dominated. In a sane state, magnetic flux is present but not dominant. The disk evolves with turbulence, and fields remain comparatively disordered. Sane is standard and normal evolution, a name that reflects how many early simulations behaved. The magnetic field is strong enough to drive MRI, but not strong enough to reorganize the entire inner flow. The result is a thick, hot plasma that flickers without settling into a single preferred geometry. Sane variability is expected to be stochastic. Polarization should fluctuate, but long-lived coherence should be rare without special geometry. In a sane-like flow, the magnetic field direction changes from one eddy to the next. Synchrotron emission can still be polarized, but the net polarization often averages down because many patches contribute at once. If a coherent swing appears, it may be brief, more like a gust than a season. In a mad state, magnetic flux accumulates near the hole. The field becomes dynamically important and can choke inflow intermittently. MAD stands for magnetically arrested disk, and the word arrested is not poetic. When enough magnetic flux piles up near the event horizon, magnetic pressure and tension can partially halt the inward drift. Gas then builds up outside the barrier until it forces its way through in bursts. MAD behavior changes what variability looks like. Strong flux can produce stronger polarization, sharper flares, and more repeatable structures. On a visualization, MAD looks like a bright inner region wrapped in ordered field lines, with intermittent surges of plasma slipping through. Those surges can create flares that repeat in character because the magnetic geometry is not reinvented every moment. The field acts like a scaffold that turbulence cannot completely erase. MAD also changes how the inner flow couples to spin. A coherent vertical field can interact with frame dragging more effectively. A spinning black hole drags space-time around it, and a large-scale magnetic field can tap that rotation. In the broadest conservative picture, this is how jets can be powered in other systems. Sagittarius A does not show a bright jet, but the coupling mechanism still matters for the inner dynamics. The documentary's tension begins here. If the anomaly is persistent, MAD-like ordering becomes an attractive conservative explanation. Persistence is the key word. Turbulence can imitate a pattern once, but persistence suggests an underlying constraint. A MAD-like field supplies that constraint because it can maintain a preferred axis and a preferred sense of twist. But MAD is not free. It requires sustained magnetic flux supply, and Sagittarius A is underfed and may not hold that state. Flux has to come from somewhere. It must be carried inward by the accreting gas, and that gas arrives in clumps from stellar winds and orbiting material in the galactic center. If the inflow is sporadic, the magnetic flux may not accumulate steadily. The system could hover near the boundary, sometimes ordered, sometimes not. So we treat sane and mad as endpoints. The real system can drift between them, and that drift can create misleading patterns. A drifting regime is a recipe for false certainty. A few hours of data might catch Sagittarius A in a temporarily ordered state. Then the next observing night might see a different personality. If we stitch those nights together, we might mistake a transient state for a permanent feature. Magnetic reconnection is the next conservative engine. It converts stressed magnetic energy into heat and non-thermal particles quickly. Reconnection is the plasma equivalent of a snapped rubber band. When magnetic field lines are forced together with opposite directions, they can rearrange and release stored energy. In the solar corona, reconnection powers flares. Near a black hole, it can do the same, but under far more extreme gravity. Reconnection can accelerate electrons to relativistic energies. Those electrons emit synchrotron radiation in infrared and millimeter bands. Synchrotron emission is a signature of charged particles spiraling in magnetic fields. The frequency depends on electron energy and field strength, so infrared light implies very energetic electrons, strong fields, or both. In Sagittarius A, the inner flow likely hosts magnetic fields of tens of Gauss, perhaps higher in compact regions. The same electrons can also produce X-rays. They can do it through inverse Compton scattering of lower energy photons or extreme synchrotron tails. In inverse Compton scattering, a fast electron collides with a low energy photon and boosts it upward in energy. The seed photons might be from the infrared flare itself or from the surrounding millimeter glow. Alternatively, if electrons are accelerated to even higher energies, synchrotron emission can extend into the X-ray band. This gives a testable expectation. If reconnection drives a flare, IR brightening should correlate with X-ray brightening in many events. Correlation is not guaranteed in every case, because geometry and optical depth can hide parts of the process. Still, if reconnection is the dominant engine, multiband partnerships should appear often. The infrared flare is the obvious beacon, and the X-rays are the harsher echo. It also gives a timing expectation. Inverse Compton X-rays can lag or lead IR, depending on where seed photons and electrons overlap. If the same region produces both the electrons and the seed photons, the timing can be nearly simultaneous. If the seed photons come from a broader region, the X-rays may lag as photons diffuse into the scattering zone. If the electron population evolves rapidly, the X-rays can peak early and fade fast. Synchrotron cooling adds another constraint. High-energy electrons cool faster, so X-ray or IR structure should evolve on predictable timescales. Cooling time is not a vague concept here. For synchrotron radiation, it scales inversely with both the square of the electron energy and the square of the magnetic field. That means the most energetic electrons burn out quickly, sometimes in minutes, unless they are continually replenished. When the anomaly appears without the expected multi-band partners, reconnection becomes less sufficient. It can still happen, but it stops being a complete story. That absence is not a refutation, but it is pressure. It suggests either that the reconnection is occurring in a way that hides its high-energy signatures, or that another geometric effect is sculpting the signal. The conservative toolbox is large, yet each tool has a distinctive fingerprint. We then consider orbiting hotspots as a conservative geometric model. A compact emitting region can circle near the ISCO and modulate what we see. The ISCO, the innermost stable circular orbit, is a boundary set by general relativity. Inside it, circular orbits become unstable and matter plunges inward. For Sagittarius A, the orbital period near the ISCO is on the order of tens of minutes, depending on spin. That timescale is suspiciously close to some reported quasi-periods. A hotspot does not need to be a solid blob. It can be a transient overdensity, a plasmoid from reconnection, or a shear compressed patch. In a turbulent flow, spot is a label for a region that temporarily outshines its surroundings. It might be a magnetic island formed during reconnection. It might be a density enhancement created by a compressive wave. It might even be a region where electrons are briefly driven into a non-thermal distribution. Orbital motion naturally creates quasi-periodicity. Doppler beaming brightens the approaching side, and dimming follows as the spot recedes. Doppler beaming is the relativistic version of a familiar effect. When the emitter moves toward us at a significant fraction of light speed, its radiation is concentrated forward. The brightness rises and the spectrum shifts. As it swings away, the brightness drops and the spectrum softens. Strong gravity adds another modulation. Lensing can magnify the spot near superior conjunction, producing peaks that look like a repeating signal. Superior conjunction means the spot is behind the black hole from our point of view. In Euclidean space, that would hide it. Near a black hole, gravity bends light around the mass, and the hidden becomes visible. The spot can brighten when it should have vanished, and that brightening can recur each orbit. But the same gravity also destroys simplicity. Differential rotation shears features into arcs, and turbulence should erase coherence quickly. Near the black hole, orbital speed changes rapidly with radius. A compact region is stretched by shear, like taffy pulled apart. Even if a spot forms cleanly, it may not remain compact for long. In a few orbits, it can become a smeared arc, then dissolve into the background. This is where relativistic ray tracing becomes central. We do not see the emitting region directly, we see its lensed images. Ray tracing is the bridge between theory and observation. It follows photons through curved space-time, accounting for gravitational redshift, Doppler shifts, and bending. Without it, we would misinterpret where the light came from and how fast the source must be moving. Light from the far side of the black hole can be bent into view. A single hotspot can appear as multiple components at once. In a visualization, the black hole is a dark disk surrounded by a glowing ring. A bright knot appears on the far side, yet a second image pops up on the near side, as if the knot has been duplicated. That duplication is not a trick. It is a consequence of photons taking different paths around the gravitational well. Some images are primary, others are higher order, created by photons that loop around the hole before escaping. Higher order images are faint, but they are conceptually important. They come from photons that skim near the photon orbit, circling the black hole one or more times. Each loop adds delay and distortion, and each loop increases the chance that the photon is captured. Those multiple images arrive with different delays. The delays can create apparent substructure in a flare, even if the local emission was smooth. A single burst of emission can be stretched into a sequence of peaks. One peak might be the direct image, another might be a lensed echo. If we do not account for these delays, we might infer multiple emission events when only one occurred. Ray tracing also explains apparent arcs. A compact region can be stretched into a curved feature by lensing near the photon orbit. The arc is not necessarily a physical filament. It can be an image artifact of space-time curvature, a projection of a compact emitter into a long, bright curve. In the most extreme cases, the arc can wrap partway around the ring, hinting at the black hole's ability to fold space into a lens. This matters for the anomaly's reported coherence. A repeating arc could be one emitter revisited, or one emitter seen repeatedly through different paths. If the same hotspot survives for several orbits, the geometry can recycle its appearance. If the spot dies quickly, lensing echoes can still create repetition. Either way, the observer sees a pattern, and the pattern can look more intentional than the plasma that produced it. Ray tracing also affects centroid motion. The brightest image can switch between lensed paths, and the centroid can jump without plasma moving that fast. The centroid is the brightness-weighted center of the emission. When one image fades and another brightens, the centroid can leap across the ring. To a naive analysis, that leap might imply a physical blob racing at impossible speed. In reality, the blob may be moving modestly, while the dominant image changes. That jump is the conservative route to impossible speeds. Apparent superluminal motion can arise from geometry and light travel time effects. Superluminal motion has a history in astronomy, from jets in active galaxies to microquasars in our own. The lesson is consistent. When light travel times and beaming are involved, apparent speed can exceed c without violating relativity. The black hole environment adds lensing to that list of illusions. The key point is not that relativity breaks. The key point is that our inference of speed depends on which image dominates at each moment. This is an uncomfortable truth for intuition. We want to track a feature as if it were a physical object. Near a black hole, the feature can be an image, and images can move in ways that matter cannot. To distinguish illusion from violation, we look for correlated signatures. True bulk motion should correlate with spectral evolution and cooling. If plasma is genuinely moving outward or inward, its density, temperature, and magnetic field environment should change. That should alter the spectrum, the polarization fraction, and the cooling behavior. A pure geometric switch, by contrast, can move the centroid while leaving the local plasma unchanged. A pure lensing switch can change position and flux with minimal spectral change. That difference becomes a diagnostic lever. In practice, this means comparing time-resolved spectra and polarization with astrometric motion. If the centroid jumps but the spectrum stays steady, geometry is implicated. If the centroid motion comes with systematic hardening or softening, physical evolution becomes more likely. Time dilation adds another layer to the illusion. Clocks run slower near the horizon relative to distant observers. In the visuals, imagine a grid of time itself stretching near the black hole. A process that takes a few minutes in the plasma's local frame can appear longer to us. This is not a cinematic metaphor. It is encoded in the gravitational redshift that also shifts photon energies. A flare that is brief locally can appear stretched. Apparent periodicity can shift if emission originates at different depths in the potential. If two flares occur at different radii, their observed durations and separations can differ, even if the local physics is similar. The deeper flare is more time-dilated and more redshifted. The higher flare is less affected. Mixing them can create a pattern that looks like a drifting clock. Time dilation also interacts with orbital dynamics. The observed period differs from the proper period, and the difference depends on radius and spin. Near the ISCO, the orbital period is already short, and relativistic effects are strong. Spin changes the location of the ISCO, pulling it inward for prograde orbits and pushing it outward for retrograde ones. That means the same observed quasi-period could correspond to different physical radii depending on spin. This can make a drifting quasi-period look more stable than it is. It can also make a stable local process look irregular from far away. If emission migrates inward during a flare, time dilation changes continuously. The observed period can remain roughly constant even as the local orbital period changes. Conversely, a stable orbit can look noisy if the dominant emission switches between radii. We then bring in frame dragging. In a spinning Kerr black hole, space-time itself is dragged around the rotation axis. Frame dragging is one of the most distinctive predictions of general relativity for rotating bodies, and it becomes extreme near a black hole. The effect is not merely that matter is pulled inward. The very definition of not rotating is altered, and inertial frames are twisted around the spin axis. Frame dragging can cause lens-thirring precession. A tilted flow or tilted hotspot orbit can precess, rotating the emission pattern. If the accretion flow is not perfectly aligned with the black hole's spin, it can wobble like a top. That wobble can rotate a bright pattern around the ring. The precession period depends on radius, spin, and the distribution of angular momentum in the flow. Precession can also rotate polarization angles. If the magnetic field is anchored to a precessing structure, the observed angle can swing coherently. Polarization is sensitive to the projected magnetic field direction on the sky. If the emitting region's geometry rotates, the polarization angle can rotate with it. A smooth swing can look like a deliberate signal, even when it is simply a precessing configuration. This is conservative but powerful. It creates a mechanism for smooth polarization rotations without requiring repeated explosive reconnection. In other words, the system can look organized without being driven by a repeating engine. Geometry can do the organizing. The black hole's spin supplies the twist, and the plasma supplies the light. Yet precession is not a universal answer. It requires a sustained tilt and a structure that survives long enough to precess coherently. Turbulence fights coherence. Shear fights coherence. If the flow is too chaotic, a tilted structure may not persist. If the tilt is small, the precession signal may be subtle. The conservative story must still match the amplitude and regularity of what is observed. Now we focus on polarization because it is the strictest witness. Synchrotron emission is polarized, and polarization encodes magnetic topology. Polarization is not just an extra data product, it is a constraint on the field geometry that produced the light. A tangled field tends to reduce net polarization. An ordered field can produce a higher polarization fraction and a more stable angle. Rapid polarization angle rotations imply changing projected field direction. They can indicate orbiting emitters, twisting fields, or propagating disturbances. A rotation can mean that the emitter is moving through a curved magnetic field. It can mean that a spiral wave is sweeping through the inner flow. It can mean that the dominant emission region is changing from one magnetic domain to another. Each possibility is conservative, but each has different implications for timescales. They can also be altered by propagation. Faraday rotation twists polarization as light passes through magnetized plasma along the line of sight. Faraday rotation is a plasma effect, not a gravitational one. As polarized light travels through a magnetized electron population, its polarization plane rotates. The amount of rotation depends on wavelength squared, which is why millimeter observations are far more vulnerable than infrared. Faraday rotation depends on electron density and magnetic field. Changes in density near the source can change the rotation measure quickly. If the inner flow becomes denser during a flare, the rotation measure can spike. If the magnetic field reorganizes, the sign and magnitude can change. In a turbulent environment, these changes can happen on short timescales, complicating the interpretation of any polarization swing. Faraday effects can also depolarize. If rotation varies across the emitting region or across bandwidth, polarization can average down. This is a subtle but crucial point. Even if each patch emits strongly polarized light, different patches can emerge with different rotation angles. When the telescope averages them together, the net polarization fraction drops. A sudden depolarization can therefore be a propagation effect rather than a change in emission physics. This creates a conservative trap. A sudden polarization change can be intrinsic, or it can be a propagation artifact within the accretion flow. The trap is especially dangerous when the source is variable. If the emission region expands, optical depth changes, and the Faraday screen changes simultaneously. The polarization behavior can look dramatic, while the underlying magnetic topology remains similar. Infrared polarization is less affected by Faraday rotation. That makes rapid IR swings harder to dismiss as propagation alone. At infrared wavelengths, the wavelength squared factor is tiny, so Faraday rotation is weak. If the infrared polarization angle rotates rapidly, the rotation is more likely to be intrinsic to the emitting region's geometry or magnetic field. That is why IR polarimetry has become such a sharp probe. Millimeter polarization is more vulnerable. It demands careful modeling of internal Faraday rotation and optical depth changes during flares. At millimeter wavelengths, the emission can be partially self-absorbed, and the polarization can flip or rotate as optical depth changes. Internal Faraday rotation, occurring within the emitting plasma itself, can further twist the signal. Interpreting a millimeter polarization swing is therefore a full radiative transfer problem, not a simple angle measurement. The anomaly is framed as a polarization puzzle. The swings appear too fast or too repeatable for a purely tangled field picture. Repeatability is again the pressure point. A tangled field can produce swings, but their statistics should look random. If the swings cluster around similar angles or similar rotation patterns, the field may be more ordered than a sane-like picture would suggest. A mad-like ordered field could help. An ordered field can maintain a preferred direction, even while brightness flickers. In a mad state, the inner region can sustain a large-scale vertical component. That component can anchor polarization, making the angle less random. Even when turbulence produces short-lived bright patches, those patches can inherit the global field orientation, preserving a sense of coherence. But ordered fields also predict other signatures. They should influence polarization fraction statistics and rotation measure constraints across epochs. A globally ordered field tends to increase the typical polarization fraction, though internal Faraday effects can suppress it. It can also stabilize the sign of the rotation measure over long periods. If the data show frequent sign reversals or wildly varying rotation measures, that would argue against a persistent ordered field. So we turn to simulations. GRMHD models are the conservative workhorse, combining strong gravity with magnetized plasma dynamics. General relativistic magnetohydrodynamics is the mathematical compromise we rely on. It treats the plasma as a conducting fluid, evolving in curved space-time. It cannot capture every kinetic detail, but it can capture the global dynamics, the turbulence, and the way magnetic flux accumulates. GRMHD can reproduce the ring scale and broad variability. It can also produce intermittent hotspots and reconnection-driven flares. In synthetic movies from simulations, the ring brightens and dims, and bright knots appear and vanish. The overall look is alive, not static. When ray tracing is applied, the simulated images can resemble what the Event Horizon Telescope reconstructs, an asymmetric ring with a shifting brightness pattern. Simulations can explore sane and mad regimes. They predict different polarization morphologies and different variability power spectra. In sane simulations, polarization maps often look patchy, with angles that vary across the ring. In mad simulations, polarization can appear more organized, sometimes showing coherent patterns aligned with a global field. The variability spectrum also differs, with MAD often producing stronger, more burst-like events. They also enable ray tracing through simulated plasma. That step turns fluid variables into synthetic images, visibilities, and polarization maps. This is where theory meets the instrument. The telescope does not see an image directly. It samples Fourier components, called visibilities, and then reconstructs an image under assumptions. By generating synthetic visibilities from simulations, researchers can test whether a given physical model would survive the same observational pipeline. In many respects, the match is encouraging. The ring diameter is robust, and the overall flicker resembles what turbulent accretion produces. The ring size is especially important because it is tied to the black hole mass and distance and to the photon orbit geometry. That robustness is a triumph of conservative physics. It tells us that, at least on the largest scales, the theory is not lost. The problem is the anomaly's specific structure. The reported coherence can require fine-tuned viewing angles, special emissivity prescriptions, or rare states. A particular viewing inclination might be needed to make lensing echoes line up just so. A particular electron heating recipe might be needed to make one region dominate the light. A particular moment in the simulation might need to be selected because the coherence is fleeting. Each requirement is plausible, but the combination becomes uneasy. Fine-tuning is not forbidden, but it is suspicious. A robust phenomenon should not depend on a narrow slice of parameter space. This is a scientific instinct built from hard experience. When a model works only under precise conditions, it may be missing a stabilizing mechanism, or it may be fitting noise. The question is not whether fine-tuning can happen. The question is whether nature would choose it repeatedly. Simulations also face microphysics limits. Reconnection and particle acceleration are often modeled with subgrid prescriptions, not first principles. GRMHD treats reconnection implicitly through numerical resistivity, and it treats electrons in simplified ways. Yet flares are often driven by non-thermal particle populations, which are kinetic phenomena. Capturing that properly may require particle-in-cell methods, which are costly and limited in scale. That matters because flares are kinetic events. The electron distribution can depart from thermal equilibrium, and that departure drives IR and X-ray output. A thermal distribution produces a predictable spectrum. A non-thermal tail produces harder emission and different polarization behavior. If the anomaly depends on a small population of ultra-energetic electrons, a fluid model that assumes near-thermal electrons can miss the decisive physics. If the anomaly depends on non-thermal electrons, a fluid-only model can miss the key ingredient. Conservative physics then becomes incomplete in practice. This is not an admission of exotic physics, it is an admission of incomplete modeling within known physics. The laws may be correct, while our computational representation is too blunt to reproduce the observed sharpness. Even within GRMHD, Turbulence can produce chance coherence. A random flow can briefly align into a spiral or arc that looks organized. In long simulation runs, rare events happen. A magnetic loop can rise and brighten. A spiral density wave can momentarily dominate the emission. A reconnection plasmoid can survive longer than average. When these events coincide with favorable lensing geometry, the result can look like a repeating structure. The question becomes statistical. How often should such coherence occur, and does the observed recurrence exceed that expectation? This is where the language of anomaly becomes precise. If a pattern appears once, it may be chance. If it appears repeatedly, the probability of chance declines. The scientific task is to quantify that decline, using ensembles of simulations and realistic observing cadences. We also confront the observational filter again. Sparse sampling and time averaging can turn evolving structure into apparent persistent modes. A telescope that observes in short windows may miss the transitions between states. Image reconstruction can also smooth over fast changes because it must regularize incomplete data. The reconstructed movie can therefore look more coherent than the underlying source, especially when the algorithm prefers continuity. Ray tracing through a variable source can produce repeated patterns. The repetition can be produced by geometry rather than by a stable emitter. A single burst can echo through lensing paths, and a single orbiting region can be seen in multiple images. If the observing cadence aligns with those echoes, the resulting time series can look like a stable oscillation. The conservative explanation is not that the source is simple, but that the mapping from source to observation is non-linear. So we attempt to subtract every illusion. We account for lensing, time delays, Doppler beaming, scattering, and reconstruction bias. Each correction is a layer removed from the signal. Interstellar scattering blurs and refracts millimeter waves as they cross the galaxy. Doppler beaming weights the approaching side. Lensing duplicates features. Time delays create echoes. Reconstruction can impose smoothness. The anomaly must survive all of these filters to remain meaningful. We then ask, what remains? The documentary frames a residual mismatch that is not a contradiction, but a stubborn remainder. A remainder is the honest outcome of a mature field. It is not the collapse of theory, it is the place where theory and data still do not fully overlap. The remainder is what motivates better simulations, better observations, and sharper statistical tests. After accounting for turbulence, reconnection, and precession, the anomaly still looks too organized. It appears too persistent to be dismissed as weather alone. The visuals linger on the ring as it subtly reshapes itself. Brightness clumps, drift, fade, and return, but the pattern seems to remember something. That impression may be misleading, yet it is strong enough to demand explanation. This is the chapter's edge. Conservative physics explains many strange signatures, including apparent superluminal jumps and rotating polarization. It explains how a centroid can leap without matter outrunning light. It explains how polarization can swing because geometry rotates, not because a new explosion occurs. It explains how a hotspot can appear twice, because space-time can fold light into multiple images. Yet the same conservative physics struggles to reproduce the anomaly's coherence without special pleading. The leftover is small, but it is structured. That structure is what makes it unsettling. Randomness has a texture, and turbulence has statistics. When the data seem to violate those expectations, even slightly, the mind reaches for deeper causes. The responsible move is to measure how strong the violation really is. That leftover returns us to the central question. Is this simply extreme black hole weather that our models still under-resolve? If so, the path forward is clear. Improve electron physics, extend simulation durations, and expand the ensemble of realizations. Observe longer, with better cadence, and compare like with like. The anomaly may shrink as the modeling becomes more faithful. Or is the baseline itself incomplete, either in plasma microphysics or in our understanding of horizons and time near them? This question is deliberately framed at the edge, not beyond it. It does not declare new physics. It asks whether the known ingredients have been assembled correctly and whether the approximations we rely on are hiding essential behavior. We end with a controlled escalation. When conservative explanations strain, scientists widen the search without abandoning rigor. Historically, this is how progress has happened in black hole astrophysics. The first hints of compact dark masses were met with skepticism. The first claims of rapid variability were questioned. The first images of horizon-scale structure demanded careful interpretation. Each time, the field advanced by tightening the conservative case before stepping outward. The next chapter crosses that threshold. Either our black hole model needs new ingredients, or Sagittarius A is not exactly what we think it is. And if that is true, the Milky Way's quiet heart may be offering something rare, a controlled laboratory where gravity, magnetism, and time reveal their sharpest edges. The anomaly has survived conservative tests long enough to widen the hypothesis space. General relativity keeps passing, yet persistence forces a harder question about what sits at the center. In practice, that means we stop asking, "Is gravity wrong?" and start asking, "Is the central object exactly what we assume?" On screen, the Milky Way's core is never shown directly because dust and gas block visible light with ruthless efficiency. We see it through proxies, stellar orbits drawn as luminous loops, infrared flares that spike and fade, and a radio ring reconstructed from sparse baselines. Each proxy is a different kind of measurement, and each one carries its own blind spots. A camera cannot look straight in, so the story is assembled from motion, timing, and bent light. The black hole assumption is not dogma, but it is the default because it works. Stellar orbits demand a compact mass of 4 million suns inside a tiny volume. The EHT ring size matches that mass scale, which is a major constraint on geometry. Even the simplest back-of-the-envelope estimate, mass divided by radius, pushes the central density far beyond any normal star. If the mass was spread out, the orbits would feel it, and the data would not forgive. Historically, this is exactly how the case was built, piece by piece, before anyone could dream of imaging a shadow. In the 1970s and 1980s, radio astronomers identified Sagittarius A as an unusually compact, bright source. Interstellar scattering blurred it, but its compactness still leaked through as a tiny, stubborn core. Then, over decades, infrared telescopes tracked the S-stars, especially S2, closing their ellipses around an unseen focus. When S2 swung through pericenter, its speed climbed to thousands of kilometers per second, and the gravitational potential looked almost perfectly point-like. The orbit was not merely fast, it was clean, as if the mass were pinned to a single point. General relativity has met that challenge repeatedly, and it has done so in the strong field margins where intuition starts to fail. The observed Schwarzschild precession of S2's orbit fits the relativistic correction expected from a compact mass. The gravitational redshift during close approach also matches the theory's predictions. These are not minor tests, they are precise checks in a regime where Newtonian gravity begins to fail. Even the transverse Doppler effect, a special relativistic time dilation, folds into the same close-pass measurements. Still, the anomaly behaves like a reminder that matching a shadow is not the whole story. A horizon is defined by what never returns, and the anomaly keeps hinting that something might. The unsettling part is not that the ring exists, but that some piece of the system seems to keep time, or keep shape, longer than turbulence should allow. When plasma should smear into noise, the signal sometimes behaves as if it remembers. A black hole's shadow is not a silhouette of the horizon itself. It is a gravitationally lensed deficit, carved out by photon capture and by the geometry of light bending. In a Kerr spacetime, the details depend on spin, viewing angle, and the emissivity of the surrounding plasma. Yet, across many models, the ring diameter stays tied to mass in a stubbornly consistent way. That consistency is why the EHT ring is so powerful. Its scale is set by gravity, more than by astrophysical mess. We call the alternatives exotic compact objects, or ECOs, because they mimic black holes. They are ultra-compact, strongly lensed, and nearly as dark, yet they may lack a true event horizon. Their motivation ranges from new particle fields to quantum gravity to dark matter configurations. The phrase mimicker is not an insult. It is a design constraint. If an alternative cannot masquerade as a black hole at large radii, it never survives the first comparison. ECOs are not invented to be mysterious, but to be testable under the same harsh constraints. They must reproduce the mass, the compactness, and the observed low luminosity. They must also predict how light, plasma, and polarization behave near an effective surface. If they cannot match the baseline successes, they are not alternatives, just curiosities. A viable ECO must fit the old evidence before it earns the right to explain the new tension. A true horizon is an absorber with no surface physics, which is why it is so clean in theory. A surface changes everything because infalling energy must go somewhere. If matter hits and heats a surface, it should radiate, and that radiation should be seen. This is the simplest thermodynamic argument in the entire debate, and it is brutally hard to evade. Gravity can hide light by redshift, but it cannot erase the accounting. To visualize the difference, imagine a stream of glowing plasma spiraling inward, threaded by magnetic fields that twist like braided wire. In the black hole picture, the stream brightens as it compresses and heats, then vanishes without a final impact flash. In a surface picture, the stream must stop, shock, and deposit energy, like a meteor hitting an atmosphere, but under extreme gravity. The visuals almost write themselves. One ending is a cut to black, the other is a collision. That becomes the first discriminant. Sagittarius A star is extremely dim for its mass, which already implies inefficient radiation. If there were a hot surface, many eco models would overproduce thermal emission. Even if the accretion rate is low, the gravitational binding energy per unit mass near the would-be horizon is enormous. A tiny trickle of matter, falling deep enough, carries an outsized energy budget. The dimness is not a vague impression, but a quantitative statement that can be expressed as an efficiency. For a given mass supply, a radiatively efficient surface would convert a significant fraction of rest mass energy into photons. Sagittarius A star instead behaves like a radiatively inefficient accretion flow, where much of the energy stays in ions, magnetic fields, or bulk motion. That makes the baseline black hole model feel natural. It also means any surface must be either extraordinarily cold, extraordinarily hidden, or extraordinarily strange. The second discriminant is the shadow. Many ECOs produce a shadow-like depression because light can still orbit and be lensed. The size can be close to a Kerr black hole, yet subtle differences appear at the photon ring. Those differences often hide in higher-order images, faint, narrow features that require extreme dynamic range to see. In practice, this becomes a challenge of calibration as much as a challenge of theory. The photon ring is not a single ring, but a stack of increasingly lensed paths. Photons can loop around the object one or more times before escaping. Each extra loop adds path length, time delay, and polarization rotation. In a true black hole, many of those paths end in capture rather than escape. In an ECO, some of those same paths may survive longer, and that survival can leave a fingerprint. The third discriminant is variability. A horizon swallows disturbances, while a surface can reflect or trap them. That difference can create late-time echoes in light curves and polarization. In the time domain, the question becomes almost cinematic. Does the flare end, or does it come back as a whisper? The answer is not just about brightness, but about whether the returning signal carries the same spectral identity. The anomaly now becomes a sharper question. If there is no true horizon, is the signal a reflection, a delayed return of energy that should have vanished? The word return matters, because it implies a causal pathway that classical horizons forbid. A horizon is not merely dark, it is one way. We start with boson stars, the cleanest field theory alternative. They are self-gravitating condensates of scalar particles, held up by quantum pressure and self-interaction. They have no horizon, and their density profile can be smooth or sharply peaked. In the simplest models, the scalar field occupies a macroscopic quantum state, like a Bose-Einstein condensate on astrophysical scales. The object is not made of ordinary matter. It is a coherent field configuration stabilized by quantum rules. The concept has a long lineage. In the 1960s, theorists explored self-gravitating scalar configurations as solutions to Einstein's equations. Later, as particle physics proposed ultralight fields, axion-like particles among them, the idea gained new relevance. A boson star becomes a way to connect a galactic center measurement to microphysical parameters. It is a rare bridge where orbital data might constrain particle mass and self-coupling. A boson star can be compact enough to lens light into a ring. It can also allow stable or quasi-stable orbits deeper than a black hole would. That changes where hotspots can persist and how long coherence can survive. The key is that the effective potential for motion can differ inside the region where a black hole would enforce instability. In other words, the interior may be strange, yet the exterior can still look familiar. In a Kerr black hole, the innermost stable circular orbit, the ISCO, marks a boundary for long-lived circular motion. Inside it, orbits plunge, and coherent structures are shredded quickly. In some boson star spacetimes, the ISCO can shift inward, or multiple stable regions can exist. That creates room for repeated, nearly periodic behavior without demanding a perfectly preserved plasma blob. The anomaly's persistence becomes less miraculous if the spacetime offers a deeper track for motion. Boson stars can produce distinctive, quasi-periodic signatures. Field configurations can support oscillation modes that modulate the gravitational potential. Those modes can imprint preferred timescales on flares without requiring a long-lived plasma blob. In plain terms, the space-time itself can ring, and the plasma responds. The flare becomes not only an outburst, but a probe of the object's internal dynamics. These oscillations are not arbitrary. They are set by the mass distribution and the scalar field's self-interaction, which determine characteristic mode frequencies. Some modes are global breathing-like oscillations, while others resemble more complex distortions. If a flare couples to a mode, the light curve can inherit a rhythm that stays stable across events. Stability is the clue, because microphysics does not drift as quickly as turbulent plasma conditions. In emission models, the key difference is what happens to infalling plasma. Instead of disappearing, plasma can pass through a dense core or interact with a steep gradient. That interaction can create repeated brightenings tied to internal oscillations. The visual is subtle. A flare that should fade cleanly instead shows a structured tail, as if the system refuses to forget. Even a small residual can matter when the baseline source is so dim. Polarization is a sensitive probe here. If emission arises from a more extended region, polarization swings may be smoother and less tied to a single orbit. If emission is concentrated by lensing near a compact core, swings can be sharp and repeatable. Polarization is geometry made visible because it encodes magnetic field orientation and relativistic transport. It is also fragile, which is why a persistent pattern is so intriguing. Near a black hole, polarization vectors are parallel transported along curved null geodesics. Frame dragging can twist the apparent direction, especially for emission close to the photon orbit. In a boson star spacetime, the transport can differ slightly, and small differences can accumulate over multiple lensed paths. The result is a statistical shift, not a single dramatic signature. This is why large samples of flares, not one spectacular event, become scientifically decisive. Boson stars also face a stability demand at 4 million solar masses. The particle mass and self-coupling must be tuned to reach this scale. That tuning links the model to early universe physics and to dark matter candidates. If the boson is too heavy, the star is too small and too massive to form. If too light, it becomes too diffuse to satisfy orbit constraints. The Milky Way's center becomes a filter that rejects most parameter space. This is where the physics beyond astronomy enters quietly. Ultralight fields appear in models of inflation, in string-inspired landscapes, and in dark matter scenarios. If the galactic center housed a boson star, it would imply that such a field not only exists, but can clump and survive in a violent baryonic environment. That is a strong claim, and it can be confronted with data. It also raises a thought-provoking question. How many galaxies would then hide similar condensates behind ordinary-looking nuclei? Next are gravastars, built from vacuum phase transitions. The idea replaces the interior of a black hole with a de Sitter-like core. A thin shell separates that interior from the exterior space-time that looks almost Kerr. Conceptually, it is a proposal that the vacuum itself changes phase under extreme compression. The object is less like a star and more like a boundary between two states of space-time. The history here is tied to discomfort with singularities. Classical general relativity predicts that continued collapse produces a region of diverging curvature, hidden behind a horizon. Many physicists suspect that quantum effects intervene before that divergence. Gravastars are one attempt to write down a concrete alternative, with an interior equation of state that resists further collapse. They keep the exterior nearly unchanged while rewriting the fate of the interior. A gravastar can be as compact as a black hole to distant observers. It can also have an effective surface at a radius only slightly larger than the Schwarzschild radius. That tiny offset matters because it permits reflection and delayed escape. The offset can be so small that, in ordinary images, the object looks indistinguishable from a black hole. In the visuals, the difference is almost cruel. A surface hidden just outside the point of no return. In gravastar scenarios, echoes become a central prediction. Light and perturbations can bounce between the photon sphere and the surface. Each bounce adds a time delay that depends on compactness and redshift. The photon sphere acts like a semi-transparent mirror because it can temporarily trap light on unstable orbits. A small fraction leaks out each time, like a dim signal escaping a cavity. Those delays could appear as repeating substructure in flare decay profiles. They could also appear as late-time polarization angle recurrences if the returning radiation is polarized. The anomaly's persistence makes this tempting, but it must match observed timescales. A real echo should not merely repeat, it should repeat with the same delay, event after event. If the delay wanders too much, the cavity starts to look like ordinary plasma chaos. A surface that close to the horizon is extremely redshifted. Any radiation emitted at the surface is stretched in time and shifted to lower energy. That can hide thermal emission, yet it also stretches echoes into potentially observable delays. What looks like milliseconds locally can become minutes for a distant telescope. Strong gravity turns short local processes into long, readable signals. The same redshift creates a constraint. If too much energy is deposited, even redshifted emission should accumulate into a detectable glow. Sagittarius A's dimness therefore limits how reflective or how emissive the shell can be. The shell cannot be both an efficient reflector and a perfect radiator without leaving a trace. The bookkeeping is simple, and the consequences are severe. We then consider fermion balls, the older compact alternative. These are dense clusters of fermionic particles supported by degeneracy pressure. They can be made of sterile neutrinos or other dark sector fermions. The analogy is to white dwarfs and neutron stars, but scaled and reimagined with different particle masses. It is an attempt to build a star out of particles that barely interact with light. Degeneracy pressure is a quantum effect with a simple translation. Fermions cannot all occupy the same quantum state, so squeezing them forces them into higher momentum states. That momentum acts like pressure, resisting gravity. It is a profound piece of physics, yet it comes with a price. To support a mass as large as Sagittarius A star, the fermions often must be heavy and densely packed. The required phase space density becomes a tight noose around the model. Fermion balls struggle with compactness at this mass scale. To fit the stellar orbit constraints, the core must be extremely small. That often requires particle masses and phase space densities that run into cosmological and structure formation limits. If the particles are too heavy, they alter early universe behavior. If too light, the core becomes too large. The Milky Way's center, again, acts like a laboratory that rejects convenient answers. Stellar orbits provide a hard boundary condition. The S-stars trace a gravitational potential that looks point-like down to very small radii. Any extended mass distribution must be smaller than those pericenter distances. The data do not merely suggest compactness, they demand it with each completed orbit. Every time S2 closes its ellipse, it tightens the allowed space for alternatives. A fermion ball that is too extended would smear the potential. It would change precession rates and orbital fits, and those changes are constrained. This makes many fermion ball models difficult to keep at 4 million solar masses. The constraint is geometric and dynamical, not aesthetic. The orbits are like a ruler pressed against the invisible mass. Yet fermion balls remain useful as a stress test. They show how far one can push dark matter into the center before dynamics pushes back. They also connect directly to the idea of dark matter cores. Even when they fail in informative ways. A failed model can still teach us which measurements are doing the real work. Dark matter cores are a broader class than fermion balls. They include self-interacting dark matter, ultralight wave-like dark matter, and mixed baryon plus dark matter configurations. The common idea is that dark matter can form a dense central object. The difference is in how the dark matter sheds energy, or how its quantum nature sets a minimum size. Each variant changes the central potential in its own characteristic way. Ultralight dark matter can behave like a coherent wave. It can form solitonic cores with characteristic sizes set by particle mass. Those cores can be compact, yet they often remain too large to mimic a horizon at Sagittarius A scales. The wave pressure that keeps them stable is also what prevents them from shrinking enough. The same physics that makes them elegant makes them hard to hide. Self-interacting dark matter can cool and collapse more efficiently. It can form compact structures if interactions allow energy loss. That possibility links the galactic center to particle physics beyond the standard model. If dark matter can scatter, radiate dark sector quanta, or undergo dissipative processes, it can behave less like a halo and more like a fluid. The implication is unsettling. The dark sector might have its own astrophysics, invisible except through gravity. Any dark matter core must still coexist with baryonic accretion. The plasma we observe must orbit within the combined potential. If the potential deviates from Kerr, orbital frequencies and lensing patterns shift. Even small deviations can matter, because the emission region sits only a few gravitational radii from the center. The inner flow is close enough that millimeters on the sky correspond to extreme curvature in space-time. That brings us back to observational discriminants. The first is thermal surface emission, which should exist if matter impacts a surface. The absence of a bright thermal component is often cited as evidence for horizons. It is not a proof, but it is a strong prior. The argument is compelling because it is rooted in energy conservation, not in detailed modeling. The argument is not absolute because surfaces can be extremely redshifted and weakly emissive. They can also be hidden by absorption and by radiatively inefficient accretion. Still, the dimness of Sagittarius A star makes the surface problem severe. The system gives us very little room to hide extra photons. If a surface exists, it must be an expert at concealment. The second discriminant is shadow size and shape. Echos can match the gross ring diameter, yet differ in higher order structure. Deviations can appear in the photon ring brightness profile and in the detailed polarization map. In images, these are not obvious distortions, but subtle redistributions of light. The eye may miss them, but statistics will not. The third discriminant is late-time echoes in variability. A surface can reflect radiation or perturbations, producing delayed repetitions. A horizon should not produce such returns, except through lensing paths that do not require reflection. The key is whether the delayed signal carries the spectral and polarization fingerprint of a reflected component. A true echo should look like the original, only fainter and delayed. The fourth discriminant is polarization behavior. Polarization encodes magnetic geometry, but it also encodes space-time transport. Echoes can alter parallel transport and the distribution of emitting regions, shifting polarization statistics. In other words, polarization is both plasma physics and geometry, intertwined. It is one of the few handles we have on the invisible architecture of the inner flow. We now connect these discriminants to the anomaly's specific features. If the anomaly is a recurring timing signature, an ECO could provide a cavity or trapped mode. That mode could keep time even when plasma turbulence should decohere. The question becomes, is the clock in the matter or in the space-time? If the rhythm survives across changing flare brightness, geometry starts to look guilty. If the anomaly is a centroid loop that repeats too cleanly, an ECO could allow stable orbits inside the black hole ISCO. That would extend the region where a hotspot can persist. It would also change the mapping between orbital phase and observed centroid. A repeated loop is not just a path, it is a statement about stability. It suggests that the flow is not merely swirling, but guided. If the anomaly is a polarization swing that repeats, an ECO could impose a preferred geometry through its surface interactions. Reflected radiation could re-enter the flow and repolarize emission. Trapped modes could also modulate the magnetic field indirectly. In that picture, the polarization is not only tracing the field, but tracing a feedback loop. The flare becomes a conversation between plasma and boundary conditions. Yet every ECO must confront the low luminosity constraint again. Infalling matter near a surface should release gravitational binding energy. If that energy is not radiated, it must be stored, advected, or hidden. Energy bookkeeping is unforgiving, even in exotic scenarios. The more compact the object, the more severe the accounting becomes. A horizon hides by definition, which is why black holes are efficient at being dim. A surface must hide by redshift, by weak coupling to radiation, or by exotic absorption. Each hiding mechanism is a prediction that can be tested. Each one leaves a different imprint on spectra, timing, or polarization. The mystery is not whether hiding is possible, but whether hiding can be perfect. We therefore examine tidal disruption and infall as a practical difference. Near a horizon, matter heats and radiates in the flow, then disappears. Near a surface, matter must decelerate and deposit energy, creating an additional emission component. The deposition could be a shock, a boundary layer, or a conversion into internal degrees of freedom. Even if the surface is exotic, the infalling plasma still has momentum that must be dealt with. The timescale of that deposition matters. If matter piles up, the surface can brighten over time. If matter is absorbed into exotic degrees of freedom, the surface can remain dark, but must still obey energy accounting. A long-lived reservoir would change the system's response to bursts, like a thermal capacitor charging and discharging. The anomaly, if it repeats, could be the discharge pattern of such a reservoir. Sagittarius A star's underfed state is crucial here. The accretion rate is low, which reduces the surface heating problem. It also makes the system more sensitive to small changes in geometry and reflection. In a brighter system, subtle echoes could be drowned in glare. Here, the darkness is not just emptiness, it is contrast. In a low accretion regime, a small reflected fraction could stand out as a structured echo. The anomaly could be a weak return signal riding on a dim baseline. That possibility raises the stakes because it turns dimness into a feature, not a limitation. It also makes the galactic center an unusually clean laboratory. When the background is quiet, even a whisper can be heard. Echo predictions can be made quantitative. The delay time depends on how close the surface is to the would-be horizon. The closer it is, the longer the logarithmic time delay becomes for a distant observer. This logarithmic scaling is a peculiar gift of strong gravity, where coordinate time stretches dramatically near the horizon. The math is technical, but the intuition is simple. Near the edge, time itself becomes sticky. That delay could fall in the minutes to hours range for Sagittarius A star. It could overlap with the quasi-periodic timescales already discussed. It could also drift if the reflecting region changes with accretion state. A drifting delay would weaken the echo-interpretation, because compactness should not fluctuate wildly. Geometry is steady, while plasma is moody. But echoes can be mimicked by plasma effects. Lensing already produces multiple images with different path lengths. Turbulent reconnection can produce repeated injections that look like echoes. Even orbiting hotspots can create secondary peaks when they pass behind the black hole and are magnified. The universe is generous with ways to fake a pattern. So the anomaly as echo must be weighed against the black hole weather described earlier. The same data that motivate ECOs can also be explained by magnetically organized states. The difference is whether a true reflection is required. The burden of proof lies with the more exotic claim. A horizonless object is an extraordinary inference, and it must earn its weight. A decisive echo would have a specific phase relationship. It would repeat with a delay that is stable across events, set by compactness rather than by plasma conditions. It would also appear across wavelengths in a consistent way. If the delay is geometric, it should not care whether we observe in infrared or radio. A plasma echo, by contrast, tends to be chromatic and state-dependent. In contrast, plasma-driven quasi-periodicity should vary with magnetic state. It should correlate with polarization fraction changes and with spectral evolution. It should also respond to accretion rate fluctuations. A plasma clock is a messy clock because the medium that sets it is constantly rearranging itself. The question is whether the anomaly behaves like a metronome or like a drummer improvising. We then connect eco ideas to cosmology because the proposed ingredients are not local. Boson stars require new scalar fields, and those fields often appear in early universe models. Dark matter cores require dark matter properties that shape galaxy formation. If the center is exotic, the implications propagate outward into the story of how galaxies assemble. A small object at the center can rewrite the narrative of an entire halo. If Sagittarius A star were an ECO made of dark matter, it would imply dark matter can collapse into compact objects. That would change expectations for central massive object growth. It would also affect how galaxies seed and evolve their nuclei. The Milky Way would become a case study in dark sector astrophysics. We would have to ask how common such dark nuclei might be and why they are not obvious elsewhere. If Sagittarius A star were a boson star, it would point to ultralight particles or self-interacting fields. Those particles could also leave imprints in cosmic structure and in gravitational wave backgrounds. The galactic center would become a particle detector by proxy. We would be reading fundamental physics off the timing of flares. The unsettling observation is that a flicker of infrared light could encode a particle's mass. If Sagittarius A star were a gravastar, the implication is deeper. It would suggest that horizons are replaced by quantum vacuum structure. That would touch the information problem and the limits of classical general relativity. It would also force a rethinking of what collapse means when space-time itself can change phase. The center would not be a place where matter ends, but a place where the vacuum reorganizes. The chapter keeps one rule clear. Any alternative must reproduce the successes of the black hole model first. It must match the mass, the compactness, the ring scale, and the broad variability. The standard model is not fragile. It is the product of many converging measurements. It has earned its status by surviving independent tests that do not share the same systematics. Then it must explain what the black hole model struggles with. It must provide a mechanism for persistent coherence without fine-tuning. It must also avoid producing thermal emission that is not observed. The anomaly matters because it is, by definition, where the baseline model feels stretched. If the anomaly evaporates with better data, the alternatives lose their best motivation. This is where polarization becomes a bridge between hypotheses. In Kerr black holes, polarization patterns are shaped by frame dragging and by magnetic topology. In ECOs, polarization can be altered by surface reflection and by modified near-field geometry. The same dataset can therefore test both plasma organization and space-time structure. A single polarized flare can carry two stories at once, and we must decide which story fits. A reflected component could rotate polarization angles in a characteristic way. It could also increase polarization fraction at late times, when direct emission fades. That late-time behavior is a specific prediction to search for. The visual cue would be a flare that seems to reappear, with a cleaner, more ordered polarization signature. Order emerging from decay would be a suspicious kind of elegance. Another discriminant is the existence of trapped modes. Ultra-compact objects can support quasi-normal modes that differ from black hole ringdown. In electromagnetic data, those modes could appear as narrow features in power spectra. They would not be as clean as gravitational wave ringdowns, but they could still stand out statistically. The key is whether the frequency is anchored to the mass scale rather than to the changing plasma conditions. The anomaly's quasi-periodic hints become relevant again. If the pattern corresponds to a trapped mode, its frequency should be stable and tied to mass. If it corresponds to plasma, its frequency should wander with state. Stability is the tell, because geometry is stable while turbulence is not. The question is almost philosophical. Are we seeing a property of matter or a property of space-time? We also consider how an ECO would affect the EHT shadow. A surface can add faint emission inside the shadow region. Even a small leak can fill in the darkness, changing contrast. In a reconstructed image, that would appear as a slightly brighter interior, or as a softened edge to the depression. The effect could be subtle, yet persistent across observing campaigns. The EHT image is time-averaged, which complicates this test. Yet polarization-resolved imaging can still constrain emission inside the ring. Future higher-frequency EHT observations can sharpen this contrast. Higher frequency means less scattering and finer angular resolution, which is exactly what the galactic center needs. As the blur of the interstellar medium recedes, the central object has fewer places to hide. Infrared astrometry adds another lever. If stable orbits exist deeper than the Kerr ISCO, centroid tracks could show different curvature and speed patterns. The anomaly's loops could then be reinterpreted as motion in a modified potential. A tiny change in potential can produce a visible change in a projected track. In visuals, a loop that closes too neatly becomes a clue that the stage itself is different. But modified potentials must still respect the stellar orbit constraints. The outer gravitational field must remain nearly identical to a black hole. That forces deviations to be confined to the innermost region. In effect, the ECO must wear a perfect Kerr mask until you get extremely close. Only in the last few gravitational radii does the disguise risk slipping. That confinement is a recurring theme. ECOs can hide differences behind strong redshift, making them hard to detect. The anomaly matters because it may be the one place where differences leak out. It is an invitation to look for the leak rather than the mask. If we cannot touch the horizon, we can still watch for what escapes its neighborhood. We return to the central question with higher stakes. If the anomaly is real and persistent, it may be the first observational handle on whether horizons truly exist. If it is not, then the black hole model survives and the anomaly becomes weather. Either outcome is informative because it tells us what kind of complexity the galactic center can support. The center is not only a mass, it is a system with behavior, and behavior can be interrogated. The chapter does not choose a winner, but it narrows what would count as evidence. A true echo would be a delayed return with a stable delay. A true surface would tend to produce thermal emission, unless hidden by extreme redshift. These are crisp criteria, even if the data are messy. The mystery is disciplined by prediction. A boson star would tend to allow deeper, stable motion and field-driven oscillation modes. A gravastar would tend to allow reflection and cavity echoes. A fermion ball, or dark matter core, would tend to alter the potential in ways stellar orbits can constrain. Each alternative carries a signature, and each signature is, in principle, observable. The challenge is not imagination, but separating signatures from the noise of an active plasma. We end with a controlled pivot back to the baseline. If Sagittarius A star is a true black hole, then the anomaly points elsewhere. It points to physics at the boundary where gravity meets quantum reality. The horizon, in that case, is not replaced, but it may not be as simple as classical theory suggests. Even a perfect black hole can have a complicated edge when quantum effects are invited to the table. That boundary might not replace the black hole, but it might modify what a horizon means. The next step is to treat the anomaly as a probe of the edge itself, not just of the object behind it. And the lingering question remains: if something can return, what exactly is it returning from? We have pushed conservative physics hard, and the anomaly still refuses to fully dissolve. We have tightened calibrations, stressed the statistics, and asked whether ordinary turbulence can mimic a clock. Yet the signal keeps returning, sometimes faint, sometimes sharp, like a pattern trying to survive our skepticism. It is time to ask what general relativity leaves out, without pretending we already know the answer. Einstein's theory is not wrong in the everyday sense. It is astonishingly successful. But success can hide omissions, especially where gravity and quantum rules overlap, and where our instruments finally reach the edge of predictability. General relativity treats space-time as smooth, continuous, and perfectly geometric at every scale. In that picture, curvature is not a force, but a shape, and matter simply follows the straightest possible paths. The equations assume that, no matter how closely you zoom in, the fabric remains differentiable and well-behaved, like an ideal surface with no grain. Quantum mechanics treats reality as fluctuating, probabilistic, and granular in how it stores information. Fields do not sit still at zero. Even the vacuum seethes with temporary excitations, constrained by uncertainty. In plain language, empty space is a restless bookkeeping system for energy and correlations, and the bookkeeping never quite stops. Both frameworks work astonishingly well, yet they disagree about what happens at an event horizon. The disagreement is not cosmetic, and it is not a preference for mystery. It is a demand for internal consistency, because the same universe must obey both rulebooks, even when the math becomes uncomfortable. A black hole horizon is the sharpest place where the two stories collide. Classically, the horizon is locally ordinary, and an infalling observer notices nothing special. If you fall freely, your local physics looks like any other patch of space-time, until tidal forces grow near the center, and even then, the horizon itself offers no warning. Quantum theory suggests the vacuum near the horizon is not empty and not perfectly calm. The horizon divides space-time into regions that cannot share signals, and that division matters for entanglement. If the anomaly is real, it may be a clue about that near-horizon region, where geometry and quantum information meet, and where inside and outside stop being casually interchangeable. Visually, the horizon is often drawn as a clean circle, a crisp edge around darkness. But the real scene is more complicated. A whirl of magnetized plasma, lensing that folds light into arcs, and time itself running unevenly. The edge is not a wall you can touch, yet it may behave like a boundary in subtle ways, the way a coastline shapes waves without being a barrier. The accessible entry point is the information paradox, stated without metaphysics. If a black hole forms from matter with a definite quantum state, that state encodes information. It includes not just mass and charge, but the detailed correlations that distinguish one arrangement from another, even when the macroscopic outcome looks identical. If the black hole later evaporates, The outgoing radiation appears thermal and information-free. Thermal radiation is defined by a few macroscopic numbers, like temperature, and it forgets the microscopic story. That forgetting is the problem. Because quantum mechanics treats information as conserved in principle, even when it is scrambled beyond recognition. Thermal radiation erases the correlations that quantum mechanics says cannot be destroyed. Entanglement is not optional bookkeeping. It is how quantum predictions remain consistent across measurements. That is the paradox, because quantum theory insists evolution preserves information in principle, and it treats loss as a breakdown of the rules. If information truly disappears, the rules that predict atoms and lasers also break. The stakes sound abstract, yet they reach into laboratory physics. If unitarity fails in one corner of nature, why should it hold everywhere else? And why should any probabilistic prediction remain trustworthy? This is why the paradox is physics, not philosophy. It threatens unitarity, which is the bookkeeping that makes quantum predictions reliable. Unitarity is the statement that probabilities add up correctly because time evolution is reversible at the level of the wave function, even when the macroscopic world looks irreversible. It also threatens locality because saving information may require non-local connections across the horizon. Locality is the idea that influences propagate through space-time step by step, not by shortcuts. The horizon becomes not just a boundary in space, but a stress test for causality, because it seems to forbid the very connections information would need. Historically, the paradox sharpened in the 1970s, when Stephen Hawking combined quantum fields with curved space-time. His calculation was conservative in method, yet radical in implication. It suggested black holes are not perfectly black, and that they radiate like warm objects, even though nothing classical escapes. Hawking's solution begins with quantum fields on curved space-time. In that framework, particles are not fundamental beads, they are excitations of fields, and particle depends on the observer. Near a horizon, different observers disagree about what counts as vacuum, and that disagreement has consequences, because the definition of no particles is not universal. Pairs of fluctuations form near the horizon, and one partner can escape as Hawking radiation. The other partner falls inward, carrying negative energy relative to infinity, which reduces the black hole's mass. The picture is often simplified, but the underlying mechanism is the mixing of field modes by strong curvature, which reshuffles what positive frequency even means. The black hole loses mass extremely slowly for large masses, and the radiation is extremely cold. Temperature scales inversely with mass, so supermassive black holes are frigid by any practical standard. Their evaporation times are so long that they dwarf the age of the universe, stretching beyond any human or even stellar timescale. For Sagittarius A, the temperature is far below the cosmic microwave background. That means the black hole is bathed in warmer radiation than it emits, so it effectively gains energy rather than loses it. Even in principle, the Hawking glow is drowned by the universe's ambient heat, like a candle submerged in daylight. The power is so tiny that no telescope can realistically detect it against any astrophysical foreground. The galactic center is bright with synchrotron emission, dust, stars, and turbulent plasma. So the anomaly cannot be direct Hawking radiation, and that constraint is decisive, because it forces us to look for subtler quantum fingerprints. If Hawking radiation is invisible here, what quantum effects could still be observable? The answer is not more brightness, but more structure in how signals propagate and decay. Instead of a glow, we look for fingerprints, timing quirks, polarization behavior, or correlations that classical horizons would wash away, especially after light has taken the longest, strangest routes. Quantum gravity could modify the near-horizon boundary conditions without producing a detectable glow. Boundary conditions are the hidden rules that tell fields how to behave at an edge, even when the edge is causal rather than material. A tiny change there can reshape late-time behavior, especially after light has orbited many times, accumulating phase shifts that act like a signature. It could also create subtle delays, reflections, or correlations that classical horizons forbid. In classical general relativity, the horizon is one way, so waves that cross it do not return. If some fraction does return, however small, the time domain becomes a place to look, because repetition is easier to test than faint brightness. The anomaly becomes a lens for asking which modifications are plausible and falsifiable. We are not free to invent any story we like, because each story must respect existing constraints. The key is to ask what would change in data, not what would sound dramatic, and to keep the burden of proof where it belongs. We now separate ideas by what they change, and by what evidence would count. Some proposals change what an infalling observer experiences at the horizon. Some proposals change what distant observers can infer from outgoing light and polarization, even if the infalling experience remains almost classical. Some proposals change the space-time metric itself, producing deviations from Kerr geometry. Kerr is the rotating black hole solution characterized by mass and spin, and it is remarkably rigid. If Sagittarius A deviates from Kerr, the deviation should echo through orbital dynamics and lensing, and it should do so in a way that is hard to hide. Each class predicts different signatures in timing, imaging, and multi-messenger data. Timing asks whether the system carries a stable clock. Imaging asks whether the shadow and ring match Kerr expectations. Multi-messenger observations ask whether gravity itself tells a different story than light, and whether the two stories can be reconciled. Black hole complementarity was an early attempt to keep both stories consistent. It says no single observer can see a violation because infall and evaporation are complementary descriptions. The idea is that quantum information is not duplicated in any operational sense, even if it appears so in a naive global picture that treats the horizon like an ordinary surface. To the distant observer, information is encoded on the horizon and re-emitted in subtle correlations. The horizon behaves like a hot membrane in an effective description, scrambling information rapidly. To the infalling observer, the horizon remains smooth and nothing dramatic happens at crossing because their local measurements cannot access the global bookkeeping. The proposal is conservative in spirit, but it demands a delicate reconciliation of viewpoints. It leans on the limits of what any one observer can measure, given finite time and finite energy. That move is elegant, yet it invites a hard question. Can consistency depend on who is watching, or must it be absolute? The firewall argument challenges that reconciliation. If information escapes in Hawking radiation while the horizon stays smooth, quantum entanglement bookkeeping fails. The tension is often framed through monogamy of entanglement, which says a quantum system cannot be maximally entangled with two independent partners, even if classical intuition wants it to be. To fix the bookkeeping, the horizon may become a high-energy boundary that breaks the smoothness. A firewall would burn infalling matter at the horizon, violating the equivalence principle. It is dramatic because it moves the quantum conflict from the singularity to the edge, turning a hidden problem into a visible rupture. The equivalence principle is the quiet foundation under general relativity's confidence. It says free fall erases gravity locally, so local experiments cannot detect a gravitational field. A firewall would mean the horizon is not locally ordinary, and that would be a profound rupture, because it would mark a place where space-time stops behaving like a smooth stage. If a firewall exists, what would it do to observable signals from Sagittarius A? It would not necessarily brighten the source, because the energy could be trapped or redshifted, but it could change how near-horizon plasma interacts with the boundary, altering variability statistics and possibly changing which trajectories survive long enough to escape. It could also suppress certain lensed paths, because photons grazing the horizon might be absorbed differently. Light near a black hole does not take one route. It takes a family of routes, including paths that loop around before escaping. If the deepest paths are selectively erased, the late time signal changes, and the change should repeat whenever geometry repeats. The most testable consequence is a deviation from classical expectations for late time tails. In many wave systems, late time decay follows predictable power laws shaped by scattering off curvature. A modified horizon could reshape that decay, subtly, but in a way that repeats, and repetition is what statistics can eventually reward. Fuzzballs offer a different escape route, motivated by string theory microstates. Instead of a smooth horizon, the black hole is a compact quantum object made of many configurations. In this view, what we call the black hole is an ensemble of horizonless states that mimic a horizon only when averaged, the way a rough surface can look smooth from far away. The classical horizon emerges only as an average description, not as a literal surface. Infalling matter interacts with microstructure before reaching a would-be horizon. The equivalence principle is modified, but not necessarily by a sharp firewall. It could be a complex, extended region, more like a dense atmosphere than a single plane. Fuzzballs predict that the near-horizon region can store and release information in complex ways. They can allow partial reflection of fields depending on frequency and microstate structure. They can also create state-dependent signatures that vary between events, yet remain anchored to mass and spin, because the overall compactness still controls the timing. For Sagittarius A, that means echoes could exist without a bright surface component. The microstructure could be dark in the sense of low emissivity, yet still reflective in a narrow, frequency-dependent way. The anomaly's persistence would then be a statistical property of microstructure, not a single mirror, and the scatter between flares would become part of the clue. Soft hair proposals take a more minimal approach. They suggest black holes carry additional low-energy quantum charges associated with symmetries at infinity. The phrase sounds whimsical, yet the underlying idea is technical. Gauge and gravitational symmetries can imply conserved quantities that are usually ignored, and those quantities can act like extra labels for what the black hole remembers. These charges could encode information without altering the classical exterior metric much. The horizon remains smooth in many versions, yet information is not lost in principle. Soft hair is subtle, and its observational consequences are correspondingly hard to pin down, because the effect lives in correlations rather than in brightness. Still, it motivates looking for correlations in radiation that are not expected from pure thermal emission. If information is carried out in delicate correlations, the signal is not a bright flare. The signal is a pattern, small, persistent, and hard to fake, especially if it recurs across independent observing campaigns. All of these ideas share a practical theme. They modify the near-horizon region in ways that might create partial reflections or trapped modes. Those modifications could produce echoes, not in the cinematic sense, but as delayed, repeating components, like a whisper returning after it has circled a vast, curved chamber. Echoes become the bridge between quantum speculation and measurable time-domain astronomy. They translate what is the horizon into what does the light curve do after a flare. That translation is powerful because it gives the anomaly a clear experimental handle, and it lets us argue with data rather than with metaphors. Echo concepts start with a simple cavity picture. Between the photon sphere and a reflective or partially reflective boundary, waves can bounce. The photon sphere is the region where light can orbit, precariously balanced between escape and capture, and it acts like a natural bottleneck that amplifies small changes. Each bounce leaks a fraction outward, producing a sequence of diminishing pulses. The pulses need not look identical because the plasma can modulate amplitudes. But the spacing between pulses is set by geometry, and geometry is stubborn, especially when it is dominated by a single compact mass. The delay time depends on how close the boundary is to the classical horizon. If the boundary sits a microscopic proper distance outside the horizon, the redshift can stretch the delay enormously. Because of strong redshift, tiny proper distances can map to long coordinate time delays, turning microscopic structure into macroscopic timing. For a supermassive object, those delays can land in minutes to hours, not microseconds. That timescale is exactly where Sagittarius A's variability lives, which is why the idea is tempting. The same strong gravity that hides the boundary also magnifies its timing consequences, and it does so with a precision that turbulence struggles to imitate. Echoes can appear in gravitational waves, in principle, and also in electromagnetic variability. In gravitational waves, the ring-down is a clean probe of boundary conditions, because it is dominated by spacetime's own modes. In electromagnetic data, the challenge is that accretion flows also reverberate, and they do so with their own messy, state-dependent delays. Plasma can create its own echoes through light travel times, scattering and orbiting hotspots. A bright knot can circle, lens, fade, and reappear with a rhythm that resembles repetition. Turbulence can also create quasi-periods that look stable until you watch long enough, and until the underlying flow reorganizes. So the key is not to see repetition once, but to see a repeatable delay with consistent scaling. A geometric echo should be achromatic in its timing, even if amplitudes vary by wavelength. A plasma reverberation should be chromatic, state-dependent, and correlated with optical depth changes, because opacity and cooling reshape what each band can see. This returns us to the Chapter 3 warning about clocks and mirages. If the anomaly is a real clock, it should survive changes in sampling cadence and reconstruction choices. If it is a mirage, its period and phase should drift with observing windows and algorithmic priors, and it should weaken when we treat red noise as the default explanation. Echo searches must therefore be done in the raw time series, not only in reconstructed images. Images are seductive, yet they are models constrained by sparse data. Timing, by contrast, can be tested against null hypotheses with fewer interpretive layers, and it can be stress-tested with synthetic injections that mimic known systematics. They must also be tested against red noise null models that mimic turbulence. Red noise is the default for accretion variability, with more power at low frequencies. Any claim of periodicity must beat that baseline, not just a white noise toy model, and it must survive choices about windowing, detrending, and cadence gaps. A second echo discriminator is polarization. Reflected or cavity-leaked components can carry a distinct polarization angle history. They can also show increased polarization fraction at late times when direct emission fades, because a smaller number of coherent paths can dominate what remains. Plasma reverberation often depolarizes, because multiple paths and Faraday rotation scramble angles. Faraday rotation twists polarization as light passes through magnetized plasma, and the twist depends on wavelength. If the polarization becomes cleaner after a delay, that is an unusual clue, because it suggests a path that avoided the most scrambling regions. So a late-time reappearance with cleaner polarization would be suspicious in a useful way. It would suggest a component that has traveled a different path or interacted with a different boundary. It would also motivate targeted campaigns that treat polarization as a timing observable, not just a static map, and that track angle evolution as carefully as flux. We also consider spacetime granularity and dispersion. If quantum gravity makes spacetime effectively granular, propagation could become energy-dependent. In some models, high-energy photons might sample the microstructure differently, accumulating tiny delays over long paths, and the strongest field trajectories would be the most sensitive. Photons of different energies could accumulate different delays along strong gravity paths. The effect is not guaranteed, and many models predict no measurable dispersion at accessible energies. But Sagittarius A offers repeated strong field paths that can be timed across wavelengths, and repetition is how tiny effects become testable. Multi-wavelength timing becomes a constraint tool. If infrared and millimeter peaks align within tight bounds across many flares, dispersion is limited. If systematic energy-dependent lags appear that cannot be explained by cooling or optical depth, dispersion gains interest, especially if the lag scales with path length rather than with flare brightness. The burden is high because plasma physics naturally creates lags through synchrotron cooling and Compton delays. Electrons radiate, cool, and shift their emission to lower frequencies over time. Optical depth can also delay the emergence of radio and millimeter emission as the plasma becomes transparent, so apparent propagation can be nothing more than evolving opacity. So the test requires simultaneous coverage and careful modeling of emission region evolution. We need to know whether a lag is a propagation effect or a source effect. That distinction is difficult, yet it is exactly where strong-field astrophysics becomes an experimental craft, because it forces us to confront both the instrument and the plasma with equal skepticism. At this point, the chapter's tension sharpens. We have a near-horizon anomaly that looks structured, yet Hawking radiation is unobservable here. So any quantum signature must be indirect, encoded in boundary conditions, correlations or propagation, and it must compete against the creativity of magnetized turbulence. The question becomes operational, not ideological. What measurement would force us to say the horizon is not smooth, or that Kerr is incomplete? In science, the strongest claims are those that specify what would change our minds, and that expose themselves to being wrong. Precision tests around Sagittarius A provide the next set of levers. Stellar orbits already confirm a compact mass, but they can also test relativistic precession precisely. Each orbit is a slow, patient experiment written in the sky over years, and the patience is part of the power. S2 gave us gravitational redshift and Schwarzschild precession, and more stars extend that baseline. The redshift test showed that time itself runs differently near the central mass. The precession test showed that the orbit's ellipse rotates as predicted by curved spacetime, and it did so with a clarity that anchored the black hole interpretation. Deviations from Kerr would show up as anomalous precession, orbital plane changes, or multipole mismatches. Kerr predicts a specific relationship between spin and the quadrupole moment, which is sometimes summarized as no hair. The goal is to measure not just mass, but the full space-time fingerprint, and to see whether that fingerprint matches the rigid Kerr template. Frame dragging is central to that fingerprint. A spinning Kerr black hole predicts Lenser-Thirring precession that depends on spin and radius. It is the twisting of space-time itself, as if rotation drags inertial frames along for the ride, subtly steering orbital planes and shifting timing in ways Newton could never anticipate. With enough well-measured orbits, we can constrain spin-induced effects in the stellar cluster. But stars are not perfect test particles, and the cluster's extended mass adds noise. Stellar interactions, unseen remnants, and distributed gas can all blur the clean, relativistic signal. So the analysis becomes a careful subtraction of astrophysical clutter. So the cleanest clock would be a pulsar in a tight orbit around Sagittarius A. A pulsar is a rotating neutron star whose radio pulses arrive with extraordinary regularity. In timing terms, it is closer to an atomic clock than to an astrophysical flare, and its stability turns space-time into something we can measure rather than infer. Pulsars are ultimate clocks because their pulses are stable and precisely timed. A pulsar near the galactic center would map space-time through timing delays and relativistic effects. It would measure Shapiro delay, frame dragging, and potentially the quadrupole moment of the central object, turning the no-hair idea into a direct numerical test. That would test the no-hair expectations of Kerr with extraordinary precision. It would also separate geometry from messy emission physics, because the pulses are not produced by the accretion flow. Yet pulsars are hard to find there because scattering and dispersion smear radio pulses, and the smearing grows worse along the crowded, turbulent line of sight. The interstellar medium toward the galactic center acts like a turbulent lens. It broadens pulses in time and blurs sources in angle, especially at low radio frequencies. Higher frequency searches help, but sensitivity and survey time become limiting, and even then the background is busy with confusing sources. The anomaly's story now intersects with this search. If the near-horizon region has quantum structure, it might also affect how plasma and fields behave. But a pulsar test would bypass plasma complexity and probe the metric directly, offering a rare chance to ask the question in a language nature answers cleanly. If Kerr passes those tests, The anomaly likely lives in plasma or in subtle horizon-scale boundary effects. If Kerr fails, the anomaly becomes a symptom of a deeper geometric deviation. Either outcome is valuable, because either outcome narrows the space of explanations, and narrowing is how mysteries become measurements. The Event Horizon Telescope is the other major lever, because it sees horizon-scale structure. Next steps are not vague upgrades, they are specific routes to falsification. Each improvement reduces a particular ambiguity that could otherwise masquerade as new physics, and each one turns a qualitative picture into a quantitative constraint. Higher frequencies, from 230 to 345 gigahertz and beyond, reduce scattering and sharpen resolution. Scattering by the interstellar medium blurs the image like frosted glass, and the effect weakens at shorter wavelengths. With sharper vision, we can compare the ring's thickness, brightness asymmetry, and stability to Kerr predictions, and we can ask whether the shadow behaves like a true absorption feature. Better baseline coverage improves imaging fidelity and reduces reconstruction degeneracies. The EHT is not a single telescope, but a planet-sized interferometer, and its aperture is a sparse network. Filling in that network turns ambiguous reconstructions into constrained measurements, and it makes it harder for algorithmic priors to masquerade as astrophysical structure. Faster snapshot imaging tracks variability without smearing, which is crucial for Sagittarius A. Unlike M87, Sagittarius A changes on short timescales, so long integrations can mix different states. Snapshot capability is a way of respecting the source's own clock, and it lets us watch the ring breathe instead of averaging it into stillness. Polarization mapping is especially important. It constrains magnetic field topology near the emission region and tests ordered field scenarios. It also constrains internal Faraday rotation and optical depth changes that can mimic geometric effects, because polarization carries memory of the plasma it crossed. If polarization patterns remain coherent across epochs, that supports persistent structure. If they decorrelate with improved cadence, that supports turbulence plus sampling bias. The difference matters, because a stable pattern is harder to attribute to chance, and it would push us toward explanations that involve geometry or boundary conditions. EHT data can also search for emission inside the shadow depression. A horizonless surface, or strong near-horizon reflection, could partially fill the central darkness. The effect may be subtle, but it should persist statistically across observing campaigns, and it should appear as a systematic excess rather than a one-off artifact. Higher dynamic range and better calibration are the requirements, not new theoretical assumptions. We are looking for small excesses and faint structures, which means systematic errors matter. In this regime, better data is not just more data, but cleaner data, because a tiny calibration bias can look like a profound physical effect. We then widen to multi-messenger probes, because some questions are cleaner in gravity than in light. An extreme mass ratio in spiral around a Sagittarius A-like black hole would map the metric exquisitely. The smaller object acts like a test mass, tracing the space-time with its orbit, and the orbit writes its story into the phase of the gravitational waves. Future LISA detections could measure multipole moments and test Kerr with waveform phasing. The waveform is a long, information-rich signal, and tiny deviations accumulate over many cycles. If the central object has a surface or quantum structure, the in-spiral could show deviations, because dissipation, absorption, and boundary conditions can alter the phasing in characteristic ways. It could also produce post-merger or late-time features that resemble echoes in gravitational waves. In gravitational waves, echoes would appear as repeating, delayed components after the main ringdown. Their presence or absence would speak directly to boundary conditions near the would-be horizon, and it would do so without the interpretive fog of radiative transfer. For Sagittarius A itself, an EMRI is unlikely in the near term, but the principle matters. LISA will observe many massive black holes, and those results will feed back into our interpretation here. Sagittarius A is our nearest laboratory, Yet it is not our only one, and comparison across systems is how we separate universal physics from local weather. If Kerr is universally confirmed, quantum structure must hide in ways that preserve the external metric. If deviations appear elsewhere, Sagittarius A's anomaly becomes part of a broader pattern. Either way, the comparison across systems is a powerful filter against local astrophysical coincidences, because it asks whether the same signatures recur under different environmental conditions. Now we assemble a roadmap that treats each explanation as a set of falsifiable predictions. We do not ask which idea is most dramatic, we ask which idea can be cornered by data. The anomaly is the narrative thread, but the endpoint is a decision tree, and each branch lives or dies by what it predicts. First branch is plasma turbulence and conservative variability. Prediction is broadband red noise with state-dependent quasi-periods that drift with accretion conditions. In this branch, the clock is an illusion produced by correlated noise and intermittent hotspots, and the most telling feature is instability, periods that wander when the flow reorganizes. Polarization swings should correlate with Faraday rotation changes and optical depth evolution. Centroid loops should weaken with better cadence and improved reconstruction constraints. Multi-wavelength lags should track cooling and Compton processes, not fixed geometric delays, and the lag distributions should broaden when the plasma becomes denser or more magnetized. Second branch is Kerr frame dragging and geometric organization within standard relativity. Prediction is preferred rotation sense and timescales tied to orbital frequencies near the ISCO. The ISCO is the innermost stable circular orbit, and its frequency depends on spin, so a consistent timescale would quietly point back to the metric itself. Polarization angle rotations should align with orbital phase and lensing geometry in ray-traced models. The pattern should scale with inferred spin and inclination and remain consistent across wavelengths. If the anomaly is geometric, X-ray counterparts may be absent because modulation is beaming, not heating, and because the same electrons can look brighter simply by pointing their emission toward us. Third branch is exotic compact object surfaces and cavity echoes. Prediction is delayed repeating components with a stable delay set by compactness, not by plasma state. Echo timing should be approximately achromatic, even if amplitudes vary with emission mechanisms, and the sequence should show a recognizable spacing even when individual pulses are distorted. Late-time polarization could become more ordered if reflected components dominate. There may be subtle shadow filling or altered photon ring brightness profiles at high dynamic range. Thermal surface emission remains a constraint, so any viable surface must be extremely redshifted or absorptive. Otherwise, it would glow too brightly and betray itself. Fourth branch is quantum horizon structure within a black hole, including firewalls, fuzzballs, and soft hair. Prediction is not a bright surface, but modified boundary conditions that alter correlation patterns. Echo-like signatures may exist, but could be weaker, more state-dependent, or microstate-dependent, which means we would need ensembles and careful statistics rather than a single dramatic detection. Statistical deviations in late-time tails, polarization transport, or higher-order image contributions become key. A firewall would imply a sharp breakdown that might suppress certain near-horizon paths. A fuzzball would imply partial reflection and complex, possibly repeatable spectral polarization fingerprints, while soft hair would imply subtle correlation structure rather than obvious timing repeats. Soft hair would imply subtle correlation structure rather than obvious timing repeats. The observational challenge is that subtle correlations demand long datasets and careful null models. The reward is that such correlations would be difficult to attribute to ordinary plasma noise, especially if they persist when the accretion flow's visible state changes. Across all branches, the decisive requirement is repeatability under improved measurement. We need long campaigns, not single nights, and ensembles of flares, not one dramatic event. We need simultaneous infrared, millimeter, and X-ray coverage to separate geometry from particle acceleration and to ensure we are not mistaking a band-limited artifact for a universal effect. We need timing analyses that treat red noise as the default and periodicity as the claim. We need polarization time series with calibrated Faraday corrections to avoid false rotations. In practice, this means building pipelines that assume nature is messy, then asking what survives the mess, and then asking again when the instruments improve. We also need to connect the anomaly to the broader galactic center environment. If the anomaly correlates with changes in accretion state, it supports plasma explanations. If it persists across states and seasons, it supports geometry or boundary condition explanations, because the environment changes while the metric does not. If it correlates with stellar wind supply or magnetic flux injection, it supports MAD-like ordering. In a magnetically arrested disk, large-scale magnetic flux can organize the flow and create more coherent structures. If it ignores those drivers, the case for deeper structure strengthens, because it suggests a clock that does not care about the weather. This is the chapter's climax because it reframes the anomaly. It is no longer only a strange flicker near a dark mass. It is a controlled test of whether horizons are smooth, whether Kerr is complete, and whether information is preserved. And it forces us to admit how little we have actually tested at the edge. The mystery stays grounded because each claim is tied to an observational lever. Each lever has a cost in telescope time, calibration effort, and statistical discipline. Yet each lever also has a payoff. Fewer stories can survive a clean, repeated measurement, and the survivors will be the ones that teach us something real. We end by returning to the Milky Way with a changed perspective. Sagittarius A is not just a point of mass, it is a boundary between known physics regimes. Around it, stars trace slow ellipses, gas streams in luminous arcs, and magnetic fields braid into patterns we are only beginning to resolve, like threads revealed when the light hits at the right angle. If the anomaly is weather, it teaches us how magnetized plasma behaves in extreme curvature. If the anomaly is a crack, it is the nearest hint that quantum gravity leaves fingerprints. Either way, solving it changes our galaxy's story because the center shapes everything around it, from star formation histories to the quiet architecture of the bulge. The next chapter will decide how to live with the answer. If the anomaly yields to better data, the black hole model becomes stronger and more detailed. If it persists and sharpens, the horizon becomes an experimental object, not a theoretical idealization, and the language of beyond Einstein becomes something we can test rather than merely imagine. At the heart of our galaxy, the equations may still be clean, but reality may not be smooth. And if space-time has seams, if information leaves traces where it should not, then the darkness at the center is not an ending. It is a beginning, inviting us to look closer and to measure more carefully than we ever have before. We return to the central question with the full case file on the table, and the evidence feels heavier now. Near Sagittarius A, something behaves like a black hole should not, at least not cleanly, not with the usual statistical mess. The baseline is still the baseline, and it is remarkably hard to escape. A 4 million solar mass compact object fits the S-star orbits, the ring diameter, and the deep gravitational time effects seen in the central parsec. Those stellar tracks, mapped over decades, trace Keplerian arcs that point to a mass packed into a region smaller than our solar system. The Event Horizon Telescope adds a different kind of constraint, one written in light rather than motion. At millimeter wavelengths, where interstellar scattering finally loosens its grip, the image resolves a bright, ring-like structure around a dark center. That ring is not a literal surface, but a photon orbit signature, light bent into a near circle by extreme curvature. Even the delays and distortions are part of the baseline story. Close to the center, clocks run slow, paths curve, and emission is Doppler boosted when plasma rushes toward us. Relativity predicts those effects with unnerving precision, and most of the time, Sagittarius A obeys. The anomaly is not the ring itself, and it is not a single dramatic outburst. It is the recurring structure in time and geometry, appearing when turbulence should erase memory and smear patterns into noise. Across campaigns, we see hints of quasi-periodic timing, centroid loops, and polarization swings that repeat too neatly. In the data, it looks like a small choreography that returns, then vanishes, then returns again. The bright region seems to slide around the ring, and the centroid traces loops that resemble an orbit viewed through a warped lens. Polarization angles rotate in a way that suggests ordered magnetic fields, not purely tangled turbulence. Some events show the signature without the expected spectral evolution or X-ray counterpart, and that absence is not trivial. In many accretion models, a flare implies fresh particle acceleration, which should brighten higher energies as electrons cool and radiate. Yet here, the millimeter and infrared can hint at structure, while the X-ray sky stays comparatively quiet. That mismatch matters because it changes what flare means in this environment. It suggests modulation by lensing and Doppler beaming, not only new energy injected into the plasma. A brightening could be a geometric alignment, an emitting knot passing behind the black hole and being magnified, rather than a sudden heating event. The anomaly qualifies as an anomaly because it resists the usual excuses that scientists reach for first. Calibration improves, scattering models sharpen, and the pipelines are cross-checked by independent teams. And yet, the pattern sometimes survives, as if the source itself is supplying a faint but persistent rhythm. We do not claim a solved mystery, and we do not pretend the evidence is immune to selection effects. We claim a narrowed mystery, with clearer failure modes for every explanation. The question becomes sharper. What can repeat near the horizon without becoming bright and without becoming obviously multi-wavelength? Now we reassemble the hypotheses into a decision tree. Each branch must explain the persistence, the intermittency, and the dimness, while staying consistent with everything we already know about Sagittarius A. The decision tree is not a verdict, but it is a discipline, an insistence that every idea pays its explanatory rent. First branch is conservative plasma physics, plus lensing, the workhorse of modern black hole astrophysics. Magnetized turbulence can produce red noise variability with occasional apparent clocks, especially when a few coherent structures survive longer than average. In a relativistic flow, even randomness can masquerade as periodicity for a short time. Hotspots can orbit for a few cycles, then shear apart as differential rotation stretches them into arcs. Reconnection can inject repeated pulses, and lensing can magnify them on schedule when geometry lines up. In that picture, the clock is partly orbital motion and partly the black hole acting as an optical instrument. This branch explains why the signal is not always present, because the flow is not always in the same state. It also explains why periods can drift with accretion rate, electron temperature, and magnetic topology near the innermost stable circular orbit. A small change in where emission originates can shift the observed timing. It struggles when the timing looks too stable across different flare amplitudes, as if the system is recalling a preferred period. It also struggles if polarization order increases late in a flare, when turbulence should be mixing and disordering the field. Stability is possible, but it becomes a parameter to tune. Second branch stays conservative on gravity but upgrades the flow, leaning into global magnetohydrodynamics. A magnetically arrested state can impose large-scale order near the ISCO, because magnetic flux piles up until it partially chokes the inflow. In simulations, that state can create persistent field geometry and coherent polarization signatures. In that picture, the clock is not a single blob, and not a lucky coincidence. The clock is a global magnetic configuration that reorganizes less often than turbulence, and it can imprint a preferred handedness on the emission. The flow becomes a structured engine, not just a boiling cauldron. It can produce coherent polarization patterns and a preferred rotation sense, even when brightness varies. It can also suppress bright X-ray counterparts by favoring geometric modulation, where beaming and lensing dominate what we see. The energy may be there, but it is not always radiated in the bands we expect. It struggles if the inferred coherence demands a cavity-like delay that ignores plasma conditions, because real plasmas are not empty and not perfectly reflective. It also struggles if timing is achromatic and fixed across wavelengths, since different bands usually sample different electron populations. A universal clock would be a strong claim. Third branch is exotic compact objects that mimic black holes, a category that exists because general relativity is tested best outside horizons. A surface or near-surface structure can reflect, trap, or delay radiation, and it can do so in a way that creates repeats. The key idea is simple in plain language. If there is something to bounce off, light can come back. Echo-like returns become the key prediction, because a stable delay would be set by compactness and redshift. The time between echoes would depend on how close the surface sits to the would-be horizon and how strongly time dilation stretches the path. That delay would not care much about the mood of the plasma. This branch can explain a stubborn clock and a structured tail, especially if the system produces faint repeats after a primary event. It can also explain why some signals reappear as dim, time-shifted versions of themselves. In the visuals, it would look like a ripple returning from the dark. It struggles against the thermodynamic constraint, which is both basic and brutal. A surface should glow if matter hits it, unless it is extremely redshifted, unusually absorptive, or coupled to hidden channels. If Sagittarius A had a surface, the steady infall of gas should leave a thermal signature. It also struggles against orbital constraints, which are among the cleanest measurements we have. Any deviation from a Kerr-like exterior must hide inside the last few gravitational radii, because the S-star orbits and the ring size already limit how different the spacetime can be. The object must mimic a black hole almost perfectly, except where we cannot easily see. Fourth branch keeps the object a black hole, but questions the horizon, which is where classical certainty meets quantum unease. Quantum gravity-inspired structure can modify boundary conditions without producing a bright surface, and that subtlety is why the idea persists. The horizon might not be a simple one-way membrane in every theory. Firewalls, fuzzballs, and soft hair-like ideas differ in mechanism, and they are not a single, unified model. They share a practical consequence: altered late-time behavior and correlations in the escaping radiation. The differences matter, but the observational target is similar. Look for departures in how information and polarization propagate. This branch can produce partial reflections, mode trapping, or statistical fingerprints in polarization transport. It can also make the deepest lensed paths behave differently, because those paths skim the region where boundary conditions matter most. In a sense, the black hole becomes a filter with a fine-grained texture. It struggles because predictions are often model-dependent, and that makes it hard to falsify cleanly. It also struggles because plasma can mimic many of the same timing features, especially when lensing is strong and the flow is patchy. The danger is mistaking complicated astrophysics for new physics. So what is most plausible right now, given the evidence we actually have? The conservative explanation still leads, with magnetized plasma plus strong lensing doing most of the work. The safest statement is that Sagittarius A is teaching us how messy matter becomes when space-time is doing the bending. The anomaly then becomes a probe of extreme weather in warped space-time, not a crack in reality yet. It is a stress test for models that assume variability is mostly stochastic and forgetful. If weather can mimic a clock, we need to know how and under what conditions. Yet we keep the door open because the anomaly targets the one place theory is least tested. The near-horizon region is where assumptions become boundary conditions, and boundary conditions are where new physics can hide. The closer we look, the more the definitions themselves start to wobble. That brings us back to cosmology, and why this matters beyond one object. The galactic center is not isolated, and its behavior shapes its neighborhood through gravity, magnetism, and intermittent outflow. Even when it is quiet, Sagittarius A is not inert. Even a quiescent supermassive black hole regulates its environment through intermittent feedback. Outflows, magnetic flux, and heating influence the nuclear gas cycle, which alternates between accumulation and expulsion. A small change in the inner flow can change how energy couples to surrounding gas. That cycle affects star formation in the central region, where dense clouds orbit in a harsh tidal field. It also affects how gas is transported inward and how the bulge and bar evolve over time. The center is a dynamical ecosystem, and Sagittarius A sits at its deepest point. There is historical context here, because the galactic center has been a proving ground for relativity in the real universe. From early radio maps that hinted at a compact source, to infrared astrometry that tracked stars at thousands of kilometers per second, each decade tightened the case. The EHT did not start the story. It sharpened it into an image. Sagittarius A is a local laboratory for a common cosmic population. Most supermassive black holes are quiet most of the time, not blazing quasars that flood the universe with radiation. If we only understand the loud ones, we misunderstand the typical life of galaxies. Quiet does not mean simple, and in some ways it is harder. Low accretion makes radiative efficiency low, but it also makes subtle geometry-driven signals easier to detect against a dim background. When the source is not saturated by brightness, structure can stand out. Understanding quiet black holes matters for cosmology because they dominate by number and by time spent in that state. They set the baseline for black hole growth histories and duty cycles, which feed into how we reconstruct the universe's energy budget. A small, systematic error, repeated across billions of galaxies, becomes a cosmological bias. They also anchor scaling relations between black holes and galaxies, such as the links between black hole mass and bulge properties. If the inner engine behaves differently than assumed, those relations inherit hidden systematics. The correlations may still hold, but our causal story could be wrong. So the anomaly is not only a curiosity, and it is not only a local puzzle. It is a lever that could refine how we model galaxy evolution across cosmic time. The Milky Way's center becomes a calibration point for the quiet majority of the universe. Now we state what would decide the case. We need horizon-scale movies with higher cadence, so variability is measured rather than averaged away. A blurred average can hide a repeating pattern, and a fast sequence can reveal whether the pattern really persists. We need improved polarization maps that track angle and fraction through flares, not just before and after. Polarization must become a time domain observable, not a static overlay. If magnetic order rises or falls systematically, that trend is a diagnostic, not a decoration. We need multi-wavelength simultaneity to test the mismatch, with infrared, millimeter, and X-ray watching together. If timing is geometric, infrared and millimeter should share structure without the same cooling lags. If timing is energetic, the spectrum should evolve in a predictable sequence. We need a galactic center pulsar to map the metric directly, because pulsars are clocks that gravity cannot easily fool. Pulsar timing would separate space-time from plasma and test Kerr multipoles cleanly. It would turn the galactic center into a precision laboratory, not just an imaging target. And we need the long game in gravitational waves, where space-time writes its own record. LISA will map central metrics through inspirals elsewhere, and comparison will discipline our interpretations here. If the universe supplies many clean tests, a single ambiguous source becomes easier to interpret. If LISA finds universal Kerr behavior, the anomaly becomes plasma plus subtle horizon physics, constrained by a stronger external standard. If LISA finds deviations, Sagittarius A becomes a nearby example of a broader pattern. Either outcome tightens the narrative because it reduces the space of plausible stories. We end with a controlled mystery, not a forced resolution. The anomaly remains a doorway, either into chaotic plasma at relativistic speeds or into deeper space-time structure that changes how horizons behave. The door is real, even if we do not yet know what room it opens into. Scientific humility is not a retreat, and it is not an aesthetic choice. It is the method that keeps wonder tethered to evidence, especially at the edge of what can be measured. In the galactic center, the edge is not metaphorical. It is an angular scale smaller than a star's apparent width. Sagittarius A is both an object and a laboratory, and the duality matters. It tests how light bends, how fields braid, and how time behaves when gravity is strongest. Each dataset is a different sense organ, and together they form a partial portrait of the invisible. The final transition is to meaning. Without pretending meaning is a measurement. The center of our galaxy is not just a destination in space, and it is not just a coordinate on a map. It is a boundary of knowledge where definitions are tested under pressure. Time, gravity, and even the word black hole are forced to earn their clarity. If the anomaly dissolves, we learn how extreme weather imitates a clock. If it persists, we learn that horizons may not be the final word. Either way, the Milky Way's heart keeps whispering the same challenge. Look closer, measure harder, and accept that reality may be stranger than our clean equations. We began with a glow where nothing should shine, and we learned that reaching the galactic center means changing languages, listening in infrared and millimeter light. We built the baseline that strong gravity demands: Kerr geometry, warped time, bent paths of photons, and then watched the data refuse to stay quiet. Across instruments, calibrations, and reconstructions, a stubborn pattern kept reappearing, not as a single flare, but as a recurring geometry. Centroid loops, polarization swings, and horizon-scale substructure that looks almost rehearsed. We tried to dissolve it into the ordinary mess of astronomy, into red noise, cadence, scattering, and bias, because anomalies are easy to invent and hard to earn. Yet the anomaly survived enough cross-checks to force the next step, exhausting conservative physics under extreme conditions, where plasma and magnetism become weather and the edge of time becomes a laboratory. The trouble is coherence, because the inner accretion flow should shear hotspots apart, scramble phases, and wash clocks into turbulence, especially near the ISCO, where gravity and motion compete brutally. If the timing is real, something is organizing the chaos. Perhaps long-lived magnetic structures, standing modes, lensing selected orbits, or a deeper coupling between fields and curvature that lets geometry outlive the particles. And then there is the mismatch that refuses to be ignored. Those events that carry the timing and shape without the spectral evolution or X-ray counterpart we would expect from violent particle acceleration. That tension hints the modulation might be primarily geometric: Doppler boosting, gravitational lensing, polarization transport through curved space, rather than a simple flare of energized electrons, and it makes multi-wavelength scrutiny the judge we cannot evade. Still, the mass, compactness, stellar orbits, and the EHT ring keep pointing back to the same conclusion, that Sagittarius A behaves overwhelmingly like a black hole, even as it toys with the cleanest version of one. So the story narrows into a decision tree with real stakes, where either we are seeing extreme space-time weather at the brink, or we are brushing against alternatives that mimic a black hole's silhouette while changing what a horizon means. What, then, is the mysterious anomaly near Sagittarius A star, and does it reveal new physics about gravity, time, and the nature of a black hole? The most honest answer is that we have not yet earned a single label, but we have earned a sharper question. Is the pattern a mirage made by our instruments and statistics, or a clock written into the geometry itself? If it is a mirage, it will break under better cadence, cleaner polarization calibration, and independent reconstructions. If it is real, it will persist across wavelengths, repeat with stable delays, and map onto the same space-time choreography even as the plasma changes its mood. In the end, Sagittarius A star may not be sending a message in words, but in constraints, forcing us to choose between messy astrophysics and a horizon that is less final than we assumed. The terrifying part is not that our equations fail, but that they may be incomplete in the one place they should have been safest, at the boundary between what can return and what cannot. So keep watching the center, because the next decisive test will not be louder, it will be cleaner. More simultaneous wavelengths, sharper polarization, longer baselines, and the patience to let a true pattern prove it is not noise. At the center of the Milky Way, our black holes seem to flicker like a wounded star, twisting light into impossible shapes, and the timing felt wrong. Now we can say the wrongness is either a fragile artifact we are finally learning to subtract, or a durable rhythm near the horizon that our baseline models cannot easily erase. Either way, the lesson is the same. When we stare into the darkest place we know, we do not just measure a black hole, we measure the limits of explanation itself. And if horizons are not the final word, then the Milky Way's heart is not an ending, but a door we have only begun to outline. Follow the next observations, and when new data arrives, ask the hardest question first. Does the pattern survive when every easy excuse is gone?